They last no longer than the blink of an eye. A whisper in the radio spectrum. A burst of energy crackling across the universe from sources so distant that the light began its journey when Earth was still young. These fleeting pulses, now known as fast radio bursts or FRBs, were unknown to science at the dawn of the 21st century. Their discovery was almost an accident, buried inside old telescope data collected years before anyone thought to look for such things. When a young astronomer named Duncan Lorimer examined archived observations from the Parkes Radio Telescope in Australia in 2007, he found something no one had ever seen: a single, isolated radio pulse that had traveled through so much intergalactic matter that it could only have come from beyond our galaxy. It lasted just a few milliseconds, but in that flicker, it emitted as much energy as the sun does in 3 days. It should not have existed, yet it did. In the years that followed, what began as a curiosity evolved into one of the most challenging mysteries in modern astrophysics. Fast radio bursts were not a one-time anomaly. They were happening everywhere. They came from seemingly random patches of sky, without warning, and disappeared before any telescope could be aimed at them. There was no accompanying explosion like a supernova, no afterglow like gamma-ray bursts, no visible light, X-rays, or gamma rays. Just a spike of energy in the radio spectrum, across a handful of milliseconds, encoded with the signature of its long voyage through plasma and gas between galaxies. The delay of high-frequency radio waves compared to lower-frequency ones betrays the density of matter they pass through. That delay, called dispersion, is how we know many FRBs come from billions of light-years away. To generate such a colossal burst of power in such a short time demands the involvement of the universe's most extreme environments. The first natural suspects were neutron stars, the crushed, super-dense remnants of dead stars with magnetic fields trillions of times stronger than Earth's. Among them, magnetars stood out as the top contenders. These are neutron stars born from especially violent supernovae, their magnetic fields so intense they warp atoms and boil space itself. If the crust of a magnetar shifts or a burst of magnetic energy is released, it could unleash an explosion detectable across the cosmos. This theory gained powerful support in 2020 when, for the first time, an FRB was detected from within our own Milky Way. It originated from a known magnetar called SGR 1935-2154. It was weaker than the extragalactic FRBs, but unmistakably the same phenomenon, bridging years of speculation with a single confirmation. But not all FRBs behave alike. Some are quiet and singular, detected once, then never heard from again. Others repeat. The discovery of the repeating class of FRBs was what truly tore open the field. In 2012, the Arecibo telescope in Puerto Rico detected an FRB that did not fade into radio history. It came back again and again. This source, named FRB 1102, was eventually traced to a small, star-forming dwarf galaxy about 3 billion light-years away. Not only did it repeat, but it also sat near a constant radio source, likely the remnants of a supernova or a nebula wrapped tightly around a young hyperactive magnetar. These repeating sources shattered the assumption that all FRBs are catastrophic events. A neutron star colliding with a black hole or a star collapsing into a black hole could explain a one-off burst, but not something that pulses hundreds of times. Even more intriguing, some repeaters have patterns. In 2020, astronomers found that one repeater, FRB 180916, emits bursts on a cycle of just over 16 days. It flares for a few days, then falls silent for 2 weeks, only to return like clockwork. Such periodicity hints at motion, perhaps a magnetar orbiting a massive companion or a precessing beam swinging like the arm of a lighthouse. Others are wilder. FRB 190520 produces bursts so frequently that it almost resembles a cosmic heartbeat, surrounded by dense plasma that makes its signal appear more distant than it is. Some repeaters appear to go dormant for months or years, then suddenly awaken in storms of hundreds of bursts within hours. The diversity of repeating FRBs suggests that there may not be a single type of engine driving them. Instead, we may be listening to a family of cosmic objects, some young and violent, some old and dying, all capable of generating energies beyond human intuition. If FRBs all came from the deaths of stars, their distribution across space would trace star-forming galaxies. But many occur in regions where stars are not being born. If they all came from magnetars, their energies should be limited. Yet a handful are so bright that they defy every known magnetar model. And if they are not exploding stars and not alien civilizations, which most scientists consider unlikely but not impossible, what are they? Some theories invoke collisions between neutron stars and black holes, crustquakes in magnetars, or even interactions between neutron stars and orbiting asteroids. Others reach deeper into speculation. Cosmic strings, relics from the first moments after the Big Bang, snapping and sending out radio energy across space-time, or white holes, theoretical time-reversed black holes that erupt rather than consume. Fast radio bursts may turn out to be not a single phenomenon, but many. What unites them is not their source, but their signal. They slice through the universe, carrying within them a record of the intergalactic medium, the vast, mostly invisible matter that lies between galaxies. Each FRB acts like a flashlight, shining through fog, revealing the otherwise invisible distribution of electrons in the cosmic web. Scientists now use FRBs to solve one of cosmology's longest-standing problems, the location of the universe's missing baryonic matter. Up to half of the matter predicted to exist in the universe had gone unseen. Not in stars, not in galaxies, not in hot gas, but in diffuse, ionized clouds between galaxies. FRBs pass through that fog and are slowed by it, allowing astronomers to weigh the universe using millisecond pulses from unknown senders. Even now, large radio observatories, such as CHIME in Canada, detect several FRBs per day. The Chinese FAST telescope has recorded thousands. Artificial intelligence is being trained to recognize them faster than human observers. Future arrays like the Square Kilometre Array, SKA, in Australia and South Africa will detect tens of thousands per year, turning what was once a cosmic rarity into a daily language spoken by the universe. They may be young magnetars or ancient neutron stars. They may be whispers from dying worlds or echoes of forces older than galaxies. But in every beat, across the darkness between stars, they remind us that the universe is not silent. It crackles with messages, brief, brilliant, and unanswered. Gamma-ray bursts are the most violent flashes of energy ever recorded in the universe, brief in time, yet colossal in power, igniting with a fury that outshines every star and galaxy combined. They erupt without warning, blaze across the sky in gamma radiation, the most energetic form of light, and then fade back into silence. Among them, the long-duration gamma-ray bursts are the giants of cosmic destruction, lasting anywhere from 2 seconds to several minutes, though most end within half a minute. They represent the final heartbeat of a massive star, far greater than our Sun, collapsing under its own weight. At first, the star swells into a red supergiant or blue hypergiant as it nears the end of its life, fusing heavier and heavier elements in its core until iron is formed. Iron cannot release energy through fusion, so the core implodes. In most cases, this collapse results in a supernova. But there is a more extreme outcome. The core continues inward, forming a black hole, while the outer layers of the star collapse in behind it. For a moment, before the star is entirely swallowed, twin jets of radiation erupt from the poles of the newborn black hole or extremely magnetized neutron star, drilling their way through the star's body at nearly the speed of light. If one of these jets is aligned toward Earth, we witness a long gamma-ray burst. Observations by satellites like NASA's Compton Gamma Ray Observatory in the 1990s and later the Neil Gehrels Swift Observatory confirmed that these bursts originate from distant galaxies, often from regions where stars are actively being born. Some of these galaxies are small and irregular, others bright and turbulent, filled with clouds of gas, igniting into new suns. Long gamma-ray bursts mark the death of the universe's most massive stars, those more than 20 or 30 times the mass of the Sun. Short-lived giants that burn hot, die young, and leave nothing behind but darkness, debris, and sometimes a quietly spinning neutron star. In 1998, astronomers finally connected the dots when a gamma-ray burst, GRB 980425, coincided with a peculiar and unusually bright supernova in a galaxy 120 million light-years away. This was the first direct evidence linking long gamma-ray bursts to collapsing stars. Long gamma-ray bursts do not merely explode, they reshape their cosmic neighborhoods. The jets they produce are so tightly focused that they can bore through the star's layers like cosmic drills, blasting matter ahead of them, producing shock waves that radiate across the electromagnetic spectrum. From gamma rays to X-rays, ultraviolet, visible light, radio. This afterglow can last days or weeks, allowing astronomers to pinpoint where in the sky the blast occurred. Sometimes the remains of the collapsing star, called a hypernova, are visible, becoming a supernova far brighter than usual because of the energy deposited by the jets. Long gamma-ray bursts often occur in the early universe, in young galaxies only a few billion years after the Big Bang. They serve as cosmic lighthouses, illuminating the distant past and allowing astronomers to study galaxies so faint and far away they would otherwise remain invisible. Despite their power, long gamma-ray bursts are rare. A galaxy like the Milky Way might only produce one every 100,000 to 1 million years. Yet across the universe, where billions upon billions of galaxies exist, bursts happen daily, seen by satellites in high Earth orbit. Their luminosity is staggering. In a few seconds, a single burst releases more energy than the Sun will emit in its entire 10 billion-year lifetime. These cosmic beacons may also play a part in extinction events. If one occurred within a few thousand light-years and pointed towards Earth, the gamma radiation could strip away parts of the atmosphere, damaging ecosystems. Some scientists have even proposed that a long gamma-ray burst might have contributed to a mass extinction on Earth hundreds of millions of years ago. But no such burst threatens us now. All known gamma-ray bursts are in distant galaxies, far beyond our reach, but close enough in light to remind us how fragile life is in a violent universe. Not all gamma-ray bursts are born from dying stars. A second family exists, shorter in duration, colder in origin, and arguably even more mysterious. These are the short gamma-ray bursts lasting less than 2 seconds, most under half a second. Their brevity is not a sign of weakness. On the contrary, they are sharper, quicker injections of energy, the final note of a long and inevitable dance between dead stars. Short gamma-ray bursts are now understood to arise from the merger of 2 neutron stars, or a neutron star and a black hole, after circling each other for billions of years. These binary systems, born from massive stars that died side by side, lose energy through the emission of gravitational waves, drawing nearer and nearer until one day, with unimaginable force, they collide. When 2 neutron stars collide, their impact is so great that space-time itself ripples outward in the form of gravitational waves, something predicted by Einstein but only recently observed. In 2017, humanity saw and heard such a collision for the first time. Gravitational waves detected by LIGO and Virgo observatories, followed by a gamma-ray burst detected seconds later by satellites. The event was labeled IBU 817. It confirmed a long-suspected truth. Short gamma-ray bursts come from the merger of neutron stars. In that moment, astronomy changed. It was no longer only the science of light, but also the science of gravity, a new era called multi-messenger astronomy. Short gamma-ray bursts are not just violent, they are creative. In the chaos following a neutron star merger, heavy elements like gold, platinum, and uranium are forged in quantities greater than all the gold mined in human history. These elements are thrown into space in an expanding cloud called a kilonova. The radioactive decay of these newly formed elements creates light detectable in infrared and optical wavelengths. It is through events like these that the universe seeds itself with the building blocks of planets, moons, and life. Every ring on a human finger, every circuit in a satellite, every vein of ore deep in Earth's crust bears the memory of a star that died, and another that was born in a burst of gamma light. And short gamma-ray bursts are more elusive than their longer cousins. They produce weaker afterglows, fade more quickly, and often occur far from the bright regions of their host galaxies, because their progenitors, neutron stars, can be kicked out of their birthplaces by supernova explosions millions of years earlier. Tracking them requires coordination between space telescopes, ground-based observatories, and gravitational wave detectors. Some short bursts show puzzling tales of X-ray light that persist for minutes after the initial burst, too long to be the result of a single collision. This has led to speculation about magnetars briefly formed in the merger before collapsing into black holes, injecting additional energy into the explosion. The study of gamma-ray bursts is the study of extremes, the collapse of the universe's most massive stars, the merger of the densest stellar corpses, the birth of black holes and magnetars, the forging of the heaviest elements, the bending of space-time. Each burst, whether long or short, is a message from a cataclysm. Together, they chart the life cycle of stars and the chemical evolution of galaxies. They remind us that creation and destruction are not opposites, but partners in the rhythm of the cosmos. When two neutron stars are born in the same stellar nursery, they begin a slow, spiraling dance that may last hundreds of millions or even billions of years, tracing ellipses around each other in silent persistence. These are not normal stars of light and hydrogen, but the crushed embers of supernovae, cores compressed so tightly that a spoonful of their matter would outweigh a mountain. Their gravity binds them in orbit, but with every revolution, they lose a whisper of energy, radiated away in the form of gravitational waves, tiny ripples that stretch and squeeze the fabric of space-time as they travel outward across the universe. What begins as a quiet duet eventually becomes a descent. The stars fall toward each other, faster and tighter until the final moments arrive. They circle one last time, contact is made, and within a fraction of a second, they collide with a force beyond comprehension. This is the birth of a kilonova. The collision of two neutron stars releases power unmatched by any ordinary supernova. For a moment, the temperature of the merging object rises to billions of degrees, enough to shatter atomic structures and fuse protons and neutrons into elements heavier than iron. Jets of matter erupt from the poles. A torus of violently rotating material forms around the collapsing core, while space itself rings from the impact. Gamma-ray detectors in orbit catch the first signal, a short, sharp burst that lasts less than 2 seconds. Astronomers now know this as a short gamma-ray burst, the cosmic gunshot announcing a kilonova. But it is in the hours and days that follow when the true wonder unfolds. The debris hurled outward in the merger, neutron-rich, unstable, incandescent, creates a glow unlike any other in the cosmos. It shines first in blue light, then red, then infrared as it cools. That optical flare is the kilonova. For years, the existence of kilonovae remained theoretical, predicted by astrophysicists in equations, but never seen. Then, on a quiet August morning in 2017, the universe whispered through the instruments of the LIGO and Virgo gravitational wave observatories. A distinct signal, a chirp in space-time itself, was detected, GW17817. Just 1.7 seconds later, NASA's Fermi telescope caught a short burst of gamma radiation from the same region of sky. Telescopes around the world turned to the galaxy NGC 4993 in Hydra. There, amid its ancient stars, a new point of light appeared, fading, changing color, exactly as theory had foretold. It was the first confirmed kilonova, the first time humans both heard and saw the death of stars in gravitational waves and light. In that single event, questions that had persisted for decades were answered. Short gamma-ray bursts are made by neutron-star collisions, and kilonovae are the cosmic forges that create gold, platinum, uranium, and the heaviest elements in the universe. In the aftermath of such a collision, the newborn object may collapse into a black hole or linger as an ultra-magnetized neutron star, a magnetar, briefly resisting collapse. The material flung outward travels at a fraction of light speed, carrying within it the raw ingredients for worlds yet to form. It is not poetic exaggeration, but scientific truth to say that the gold in a wedding ring, the iodine in the human body, the uranium buried deep in Earth's crust, were once birthed in the incandescent ashes of a kilonova. Every atom heavier than iron owes its existence to either these mergers or the rarest types of supernovae. In the elemental language of the cosmos, Kilonovae speak the words of creation written in fire. Not all mergers are equal. When a neutron star collides with a black hole, the outcome depends on appetite and geometry. If the black hole is too massive, it swallows the neutron star whole, leaving behind little more than darkness. But if the conditions are right, if the neutron star's orbit is grazing, if the black hole spins rapidly, the neutron star may be torn apart before being consumed. Its matter forms a spiral of glowing debris, circling the black hole like water around a drain, before being flung into space. These neutron star-black hole mergers may also produce kilonovae, but fainter, their light dimmed by the insatiable gravity of the black hole. Where kilonovae speak of creation through collision, another phenomenon tells of destruction by consumption. Tidal disruption events, when a star ventures too close to a supermassive black hole. At the heart of nearly every large galaxy lies such a black hole, millions or billions of times the mass of the Sun, dormant except when a wandering star crosses its path. As the star approaches, immense tidal forces, gravity pulling more strongly on one side than the other, begin to tear it apart. First, the star stretches, then it unravels. In a final act of celestial violence, it is shredded into a stream of gas. Half of that gas is thrown into space. The other half spirals inward, forming an accretion disk around the black hole, glowing with the heat of infalling matter. For weeks or months, this light shines across the universe. The black hole feeds. The galaxy briefly awakens. Then it darkens once more. Tidal disruption events, or TDEs, were once purely theoretical. Now, telescopes like the Zwicky Transient Facility and Pan-STARRS detect them regularly, catching galaxies in their brief moments of hunger. Some TDEs emit mostly ultraviolet and optical light, their glow soft and sustained. Others erupt in X-rays, betraying jets of matter shot from the black hole's poles. A rare few produce radio waves, the echoes of shock waves through surrounding gas. In 2019, astronomers caught a TDE happening in real time in a galaxy 375 million light-years away. It was named AT2019 QIs, and for the first time, observers followed a star's death from the moment it began falling apart until its remnants were devoured. What makes TDEs so compelling is not only their violence, but their intimacy. In a kilonova, two corpses collide. In a supernova, a star dies of internal collapse. But in a tidal disruption event, a living star is torn apart by a force it cannot understand. The black hole does not swallow it all at once. It pulls at it, thread by thread, until nothing remains but a glowing spiral. Some TDEs fade quietly. Others flare again months later as leftover gas returns in delayed streams. These flickers and echoes provide astronomers with a rare view of black hole physics, how matter flows, how jets are launched, how gravity warps time and space near the event horizon. Recently, new mysteries have emerged. Some TDEs emit periodic flashes in ultraviolet or X-ray light, as though something survives the encounter, orbiting the black hole and dragging debris behind it. Others show signs of heavy elements that should not exist unless a star's core was exposed, hinting that some disrupted stars may have been giants with burned-out hearts. A few TDEs even appear to be obscured by dust, their light re-emerging in infrared as it heats surrounding clouds. Each one adds a new puzzle piece to our understanding of how galaxies grow and how black holes feed. Kilonovae and tidal disruption events occupy opposite sides of a cosmic mirror. One shows how the universe creates heavy elements through the union of dead stars. The other reveals how it destroys living ones through the appetite of black holes. Yet both remind us of the same truth. Energy and matter flow in cycles through space and time, born in fire, unmade in gravity, returned to the stars once more. In their light, we glimpse not only the extremes of physics, but the quiet, relentless order of the cosmos. They are rare, unpredictable, and distant, yet their consequences are everywhere, in rings of gold, in dust of galaxies, in atoms that shape life. To study them is to listen to the heartbeat of the universe, pulsing across the vastness of night. When a star dies and collapses into a neutron star, what remains is one of the densest objects in existence, a city-sized sphere holding more mass than the Sun. But among these neutron stars lies an even rarer, stranger breed, known as magnetars. They are the titans of magnetic fury, their fields so strong that they could erase the data on every hard drive on Earth from halfway across the moon. Their energy is not steady or patient. It seethes beneath their crusts like pressure beneath a planet's surface. And when that crust gives way, the result is a magnetar giant flare, one of the most violent bursts of energy our galaxy can produce. The first of these flares ever detected came unexpectedly in March of 1979, when a wave of gamma rays swept through the solar system, first striking the Venus orbiter Pioneer and then several satellites near Earth. At first, scientists thought a nuclear war had begun. The signal was that bright, that sudden. But the direction of the burst traced not to Earth, but to a small, otherwise unremarkable region of the sky in the constellation Dorado, the site of the Large Magellanic Cloud. There, hidden inside the supernova remnant N49, was a magnetar. In less than a second, it had released as much energy as the Sun emits in 100,000 years. Giant flares occur when the magnetic field of a magnetar twists and distorts until the star's crust can no longer contain it. The crust cracks, a true quake on a cosmic scale, and magnetic energy explodes outward in a beam of gamma and X-rays. For a brief instant, the magnetar outshines every star in its galaxy. The shockwave of radiation sweeps through space, bouncing off the magnetosphere and racing outward faster than any other process in nature can transmit energy. Though the flare itself lasts mere seconds, its echoes can persist for minutes as the field rings like a struck bell. The most powerful one ever observed, in December 2004, from the magnetar SGR 180620, was so intense it caused Earth's ionosphere to vibrate and disrupted satellite communications. Had it been just a few light years away instead of 50,000, the effects could have stripped our planet's atmosphere. Each giant flare reveals the terrible tension between order and chaos inside a magnetar. The crust, only a kilometer thick, is composed of neutron-rich nuclei packed in a crystalline lattice, overlaying a core of superfluid neutrons and exotic particles. The magnetic field threading through this structure is 1 trillion times stronger than anything humans can create. When the field shifts, the crust snaps, releasing pent-up magnetic energy that accelerates particles to near-light speed. The flare that follows can trigger smaller aftershocks, bursts of lower energy that ripple outward for days or weeks. Observatories like Fermi, Swift, and NICA have catalogued dozens of such magnetar flares, each one a fleeting reminder of how unstable and dynamic these stars remain long after their births in supernova explosions. But the story of magnetars is not only one of violence, it is also one of connection. When astronomers detected a fast radio burst in 2020 from the magnetar SGR 1935-2154, it became clear that these strange objects could also be the engines of the mysterious radio pulses that sweep through the cosmos. Magnetar flares might, therefore, be one of the missing links between transient gamma-ray phenomena and the mysterious millisecond radio signals that have puzzled astronomers for years. The same cracking crust that triggers a giant flare could generate powerful electromagnetic shocks that escape as radio flashes detectable across galaxies. Yet not every disturbance in a magnetar produces a giant flare. Many are smaller, subtler, born from deep within the star's crust, a phenomenon known as a starquake. The comparison to earthquakes is apt but insufficient. On Earth, a quake releases strain, built up by the shifting of crustal plates. On a magnetar, the strain comes from the twisting of magnetic fields so intense that they warp matter itself. The neutron star's rigid surface bends under the pressure until it fractures. A region just a few hundred meters wide can release energy equivalent to all the nuclear weapons on Earth detonating at once. The sudden jolt can alter the star's rotation by measurable amounts, producing glitches that astronomers can detect with millisecond precision. Starquakes explain much of the restless variability seen in magnetars. They can trigger bursts of X-rays or gamma rays, each lasting less than a second, or generate the slow flicker of soft gamma repeaters that pulse for days at a time. The quake rearranges the magnetic field, changing how it channels charged particles around the star. Some models suggest these rearrangements can even produce temporary magnetospheric loops, structures reminiscent of the coronal loops seen on the Sun, but magnified by unimaginable intensity. When those loops snap, they emit both radiation and radio waves, linking the smallest crustal movements to some of the most energetic events in the cosmos. In the deepest sense, a magnetar is a conversation between gravity and magnetism. Gravity crushes matter to densities where atomic structure ceases to exist, while magnetism tries to tear that order apart. Every flare, every quake, is a brief moment when magnetism wins. Over thousands of years, the magnetic field slowly decays. The star's outbursts diminish, and what remains is an aging neutron star, silent but still heavy with secrets. These decaying giants may be the source of mysterious X-ray transients and could eventually fade into cold, dark spheres, their energies finally spent. From giant flares that shake the heavens to starquakes that rattle the bones of matter, magnetars remind us that the universe is not static, but alive with stress and release. Their tempests are not random. They are the language of extreme physics written across a neutron crust. When their energy surges outward, it travels through light years of empty space to strike a detector on Earth, a whisper from a collapsed sun telling us that even in death, stars can still rage. They are the brightest stellar explosions the universe has ever revealed to us. Superluminous supernovae, eruptions so intensely radiant that they can outshine an entire galaxy for weeks. Ordinary supernovae, violent as they are, cannot compare. In a typical core collapse supernova, a massive star reaches the end of its life and detonates with the power often of billions of suns. But superluminous supernovae exceed this by factors of 10, sometimes 100, flooding the cosmos with light so powerful that telescopes millions of light-years away detect them with ease. They do not occur often. For every 10,000 regular supernovae, perhaps one will cross the threshold into superluminous territory. Yet these rare titans reveal something extraordinary about how stars die, and how the universe creates the elements and energies that seed galaxies with the stuff of planets, atmospheres, and life. What drives their brilliance remains debated, but three main mechanisms are believed to be involved. In some cases, a newly formed magnetar, a neutron star spinning hundreds of times per second, swaddled in a magnetic field a trillion times stronger than Earth's, forms at the core of the explosion. As this magnetar slows, it releases rotational energy into the expanding supernova debris, electrifying it like a filament infused with current, making the dying star blaze with unnatural luminosity. Other superluminous supernovae come from stars wrapped in thick shells of gas expelled shortly before their deaths. When the supernova explosion crashes into this material, the collision produces powerful shock waves that convert kinetic energy into light, creating an enormous, sustained flare. And then there are those that might be the last breath of the most massive stars of all. Stars so heavy that when their cores fill with gamma radiation, light transforms into particles, pressure plummets, and the star collapses while simultaneously burning in an uncontrolled thermonuclear inferno. These are called pair instability supernovae, and they leave no remnant behind. No neutron star, no black hole, just a cloud of elements hurled into space. Superluminous supernovae were first clearly identified only in the last 2 decades, thanks to wide-field surveys scanning the sky each night for transient phenomena. They often occur in small, low metallicity galaxies, places where stars retain more of their primordial hydrogen and helium, unpolluted by heavier elements forged in previous generations of stars. This hints at their origins in massive stars reminiscent of those born in the early universe, making superluminous supernovae possible fossils of cosmic youth. One such explosion, SN 2006 GY, erupted in the Perseus galaxy cluster and became one of the most luminous events ever recorded. For months, its brightness rivaled its host galaxy. Another, SN 2007 BI, revealed chemical signatures suggesting a pair instability origin, perhaps from a progenitor star with nearly 200 times the mass of our Sun. These discoveries expanded the known boundaries of what a star could do when it dies. Yet even among these monsters lies a class stranger still: fast blue optical transients, or FBOTs. They appeared suddenly in astronomical data around 2018, the first and most famous being nicknamed the Cow, officially designated AT2018 Cow. Unlike superluminous supernovae, which rise to peak brightness over days or weeks, the Cow reached peak in just 2 days. It glowed intensely in blue and ultraviolet light, indicating extremely high temperatures exceeding 30,000 degrees Celsius. It then faded rapidly, its light curve declining faster than any known supernova type. Embedded in this optical storm were powerful X-rays and radio emissions, suggesting a compact central engine, an ascent black hole or magnetar, still actively injecting energy into the expanding debris. The Cow was both familiar and alien. It occurred in a relatively nearby galaxy just 200 million light-years away, close in cosmic terms, which allowed an unprecedented level of observation. its spectrum showed little evidence of hydrogen, meaning the star that exploded had already shed its outer layers. What made it unsettling was the speed and intensity of its evolution. Traditional supernova models could not fully account for its behavior. Within weeks, another similar event was found. Astronomers named it A2018 GRP. Then more followed. AT2019 QIZZ, ZTF on scene, ABV Kabul away. Colloquially called the koala, and others more whimsically named the camel, and the CSS 11610TN. Fast blue optical transients do not simply explode, they erupt as though something inside is tearing space itself. Some theories suggest a massive star collapsing directly into a black hole while ejecting only a thin shell of material. Others propose a newborn black hole or magnetar driving jets of energy that rip through the star's last layers. There are even models where a star is partially shredded by a black hole, a sort of mini tidal disruption event, producing an optical flare with properties that mimic both supernovae and TDEs. The truth may be that FBOTs are not one phenomenon, but several. Their shared feature being speed. They burn fast, they burn hot, and they vanish before the universe has time to blink. What binds superluminous supernovae and FBOTs is the sense that they mark the limits of how wildly a star can die. They transform matter into light with astonishing efficiency. They create exotic remnants, magnetars, black holes, perhaps something in between. They seed space with the heaviest elements, including those essential to planets and life. Yet they also challenge our models. Their light curves decline too fast for radioactive decay alone. Their spectra often lack clear layers, as though the explosion scraped the star clean of identity. In the case of the cow, afterglow observations revealed material expanding at 1/10 the speed of light. It embedded with a compact source emitting X-rays like a heartbeat in the wreckage. The James Webb Space Telescope and upcoming instruments like the Vera Rubin Observatory will reveal more of these luminous enigmas. Already, Webb has begun to detect infant galaxies lit by ancient superluminous supernovae, their ashes enriching the cosmos. Some scientists speculate that the first stars, population 3 giants, may have ended their lives in pair instability supernovae, their explosions lighting up a universe still dark with hydrogen. If so, modern superluminous supernovae are echoes of that forgotten age, and FBOTs, still so few in number, may become more common as sky surveys grow deeper and faster. If their origin lies in black holes being born in plain sight or dying stars collapsing incompletely, then every one of them is a window into nature's most urgent moments. They might even explain some fast radio bursts if their engines survive the explosion long enough to produce radio pulses. Or perhaps they herald a class of stellar deaths we have not yet fully imagined, where fire, gravity, and magnetism collide in ways brief but unforgettable. In the end, both superluminous supernovae and fast blue optical transients are cosmic exclamation points, swift declarations that the universe is still experimenting with how stars live and how they die. They remind us that the night sky, though quiet to our eyes, is alive with catastrophes so bright they could light a galaxy, yet so brief we could miss them if we blinked. Their light travels millions or billions of years to reach us, carrying within it not just spectacle, but testimony. testimony that in death, stars do not simply vanish, they perform. And in their performance, they write the next chapter of the cosmos. At the heart of many galaxies lies a dormant monster, a supermassive black hole, millions or billions of times more massive than the Sun, silent until matter drifts too close. When that happens, gravity seizes it, tears it apart, and feeds on it. The material spirals inward, forming a radiant disk so hot it glows with energy across the electromagnetic spectrum. When this happens steadily, the center of the galaxy ignites into what astronomers call an active galactic nucleus, or AGN. For decades, the universe seemed to follow a rule. A galaxy's nucleus was either active or quiet, a switch locked in one position for tens of thousands of years. But then, scientists discovered something unsettling. Some AGN change, fast, too fast. Within months or years, quasars that had been blazing with light dimmed until their cores appeared silent, as if the black hole had simply stopped feeding. Others, just as mysteriously, brightened, waking from darkness into fierce radiance. These became known as changing look AGN. A changing look active galactic nucleus challenges everything once assumed about the pace of galaxies. For an object so large, so deep within its host galaxy, to drastically shift its brightness within a human lifetime seemed impossible. The first such object was noticed in the late 20th century, but it was not until modern instruments and long-term sky surveys arrived that the phenomenon became undeniable. A quasar catalogued as SDSS J01590033 was observed to fade dramatically in optical light over less than 10 years. Its broad emission lines, signatures of fast-moving gas close to the black hole, evaporating from its spectrum. Another, Mercerc 1018, dimmed by a factor of 7 in optical light over 5 years, only to brighten again years later. Initially, astronomers thought clouds of dust might be passing in front of the black hole's core, blocking its light as the moon passes across the sun. But the spectral signatures told a different story. The gas responsible for the broad emission features, material whipping around the black hole at thousands of kilometers per second, was vanishing. This could only happen if the black hole's fuel supply had been cut off, or the disk itself had changed its structure. That meant the central engine of a galaxy could flicker or shift state, not over cosmic time, but over a span shorter than a career. A phenomenon once thought to require millennia was unfolding before human eyes. How this happens remains a matter of debate. One theory suggests that the flow of gas onto the black hole undergoes abrupt changes when the accretion disk becomes unstable. Too much matter in the inner regions, or too little, could alter how efficiently the black hole feeds, causing its output to surge or collapse. Another theory ties changing look AGN to tidal disruption events, when a wandering star is torn apart by the black hole, creating a temporary flare of activity that fades once the debris is consumed. Others consider magnetic instabilities in the disk as tangled fields shift and intensify, briefly transforming the way energy escapes from the black hole's grasp. Yet the timescale still puzzles astronomers. For a supermassive black hole to starve in just a few years implies that its food supply, gas drawn from the galaxy, must be delivered not as a steady stream, but as unpredictable, chaotic fragments. As astronomers monitored these unpredictable giants, they discovered a second, even stranger rhythm echoing from galactic cores, quasi-periodic eruptions, or QPEs. Unlike the grand transitions of changing-look AGN, QPEs are compact, recurring flashes of X-rays that blaze from the heart of certain galaxies at intervals as regular as a heartbeat. They are brief, each lasting tens of minutes to a few hours, but they return with uncanny timing, sometimes every few hours, other times every few days. In 2019, an object in the galaxy GSN 069 captivated astronomers by erupting every 9 hours. Its flares were so regular that someone unfamiliar with the source might have mistaken them for a signal created by intelligent life. But their origin appears to be no message. Instead, QPEs seem to come from matter repeatedly falling toward a supermassive black hole, heating to millions of degrees as it does. In one leading theory, a small star or white dwarf is trapped in an extremely tight orbit around the black hole. Each time it swings close to the event horizon, its outer layers are stripped away by tidal forces, feeding the black hole in pulses. The black hole responds with an outburst of X-rays before the star swings outward again. The cycle repeats until the star is entirely consumed. Another hypothesis imagines dense clumps within the accretion disk stalling and then plunging inward in rhythm, like stones skipping along the surface of a whirlpool. Either way, QPEs require a delicate interplay between gravity, angular momentum, and plasma physics occurring in the innermost regions of the accretion disk, just a few Schwarzschild radii from oblivion. Some QPE sources are even more perplexing. Their eruptions are not only regular, but shrink and grow in intensity, as if another object, perhaps a second star, influences the process. One flare will blaze brilliantly, the next will be faint, the third, brighter again. In some galaxies, two distinct rhythms are observed simultaneously, suggesting that multiple orbits or instabilities coexist close to the central black hole. These aren't random fireworks. They are precise, as if some hidden clock is keeping time at the edge of space-time. What connects changing-look AGN and quasi-periodic eruptions is that both reveal the supermassive black hole, not as a static monster, but as a variable, breathing thing. At the centers of galaxies, gravity compresses and twists gas into structures more extreme than anything elsewhere in nature. Magnetic fields rise and convulse. Matter accelerates to nearly the speed of light. Light, bent by gravity, loops around the black hole before escaping. In this environment, changes can happen fast, faster than once believed. A cloud of gas, drifting inward, can revive a dead galactic core. A shift in the magnetic structure of the accretion disk can mute a quasar that once lit up the cosmos. A captive star, enduring orbit after orbit, can feed the black hole in delicate increments until it vanishes. Humanity now possesses instruments sensitive enough to witness these changes as they occur. The XMM Newton and Chandra X-ray observatories have recorded the slow rise and fall of QPEs. Optical sky surveys like Pan-STARRS and the Zwicky Transient Facility catch changing-look AGN switching states in real time. Soon, the Vera Rubin Observatory will photograph the entire sky every few nights, capturing the universe in motion. What was once seen as static is now being revealed as alive. Black holes, once thought to be eternal fixtures in galaxies, are instead showing themselves to be dynamic engines tuned to the unpredictable rhythms of gravity and gas. Their feeding habits are erratic. Their light flickers. Their hearts beat. Changing look, and whisper of feast and famine across years. Quasi-periodic eruptions tick and pulse across hours. Both are expressions of the same truth, that even on the largest scales, the universe is restless. Nothing is fixed. Not the stars, not the galaxies, not even the darkness at their centers. Black holes have long been divided into two great families. There are the stellar mass black holes, born from the collapse of massive stars, usually weighing between a few and a few tens of solar masses. And then there are the supermassive black holes, enthroned at the centers of galaxies, millions or billions of times the mass of our Sun. But for decades, there has been suspicion of a third, elusive kind in between, a missing link in the black hole hierarchy. These are the intermediate mass black holes, neither small nor cosmic giants, but weighing somewhere between 100 and 100,000 solar masses. Their existence would answer many questions: how supermassive black holes first formed, how globular clusters evolve, how galaxies assembled themselves. But finding them has been like chasing ghosts. They do not shine, they give off no light, and unlike their supermassive kin, they do not sit at the luminous heart of galaxies for our telescopes to conveniently observe. If they exist, most must drift in darkness, hidden inside globular clusters or orphaned in intergalactic space. The first hints of their presence came from objects that radiated more X-rays than stellar mass black holes should be capable of, ultraluminous X-ray sources, or ULXs. Some astronomers suspected these to be black holes a few hundred times more massive than the Sun, devouring gas from nearby stars. Others argued these were simply stellar mass black holes feeding in unusual ways. The debate stretched on. Then, in 2004, the Hubble Space Telescope detected a strange object in the globular cluster G1 in the Andromeda Galaxy. Its stars moved as though orbiting something around 20,000 solar masses. Observations of the cluster M15 in our own Milky Way suggested a similar hidden mass. These were tantalizing clues, but still no direct proof. Only when gravitational wave astronomy was born did the universe begin to speak more clearly. In September 2020, the LIGO and Virgo detectors recorded the merger of two black holes. One, about 66 times the mass of the Sun, the other about 85, both themselves massive enough to be troubling. Their collision formed a single black hole, weighing about 142 solar masses. It was given the name GW-0521. This was the first confirmed intermediate mass black hole ever detected. It did not shine. It rang through the fabric of space-time. Others have followed, some in the hundreds of solar masses. Yet this still raises more questions than it answers. Where did they come from? Are they the corpses of the universe's first stars, those enormous metal-free giants called Population 3 stars? Or did they grow slowly, one stellar merger at a time, in the crowded hearts of star clusters? Perhaps some dwell not at the centers of galaxies, but adrift, relics of ancient collisions between dwarf galaxies now swallowed by larger ones. Though unseen, intermediate mass black holes may betray their presence through the ways they bend space. Stars orbit faster near them. Gas heats as it falls inward. If one lies at the center of a globular cluster, it subtly alters the cluster's shape, squeezing stars toward the core. With better instruments, astronomers are watching. The James Webb Space Telescope peers into star clusters in distant galaxies, searching for motions that cannot be explained by visible stars alone. Future missions like LISA, a space-based gravitational wave observatory, will be able to detect the slow wails of black holes thousands of times the mass of our Sun, colliding in the hearts of merging galaxies. If Webb and LISA succeed, the black hole family tree will finally have its middle branch. Yet for all their mystery, intermediate mass black holes follow the same fundamental laws as all others. At the heart of a black hole lies a boundary beyond which light itself cannot return, the event horizon. It is not a surface in any physical sense. Nothing solid lies there. It is instead a point of no return, where gravity curves space-time so steeply that all paths forward lead inward. For an outside observer, light emitted just above the event horizon appears to slow, redden, and fade, never quite escaping. For the object falling in, time stretches, space shortens, and the fabric of reality bends into a funnel from which there is no escape. Surrounding this invisible threshold is something that can be seen: the photon ring. If one could look directly at a black hole, one would not see a hole, but a ring of light, encircling darkness like a halo. This ring is made up of photons, particles of light trapped in unstable orbits around the black hole. Some circle it once before flying off. Others circle many times before escaping toward distant observers. The closer light passes to the event horizon, the more its path is bent by gravity. Those that pass at the precise radius of the photon sphere, about 1.5 times the Schwarzschild radius for a non-rotating black hole, loop around before escaping to the universe. This accumulation of bent paths produces a bright, narrow ring, sharp, delicate, and whisper-thin. For centuries, this was only theory. Then, in April 2019, the Event Horizon Telescope collaboration revealed the first direct image of a black hole's shadow. It was the supermassive black hole in the galaxy M87, 55 million light-years from Earth. A glowing donut of radio light surrounded a dark center, the shadow cast by the black hole itself, caused by light being swallowed beyond the event horizon. The bright ring, slightly lopsided, hinted at the black hole's spin. In 2022, they produced a second image, this time of Sagittarius A, the black hole at the center of our own Milky Way. It was harder to catch, its appearance fluctuating in minutes as gas swirled around it. Yet still, the ring appeared, light bent by gravity, into a circle around darkness. What these images show is not the black hole, but its silhouette. The photon ring is not a physical structure, but a gravitational mirage, a lens effect caused by space-time's curvature. To photograph it, telescopes around the world were linked into a planet-sized interferometer, able to detect detail equivalent to seeing a grapefruit on the surface of the moon. The result was both a triumph of technology and a vindication of Einstein's theory of general relativity. Everything about the ring, the radius of the shadow, the way light curves, the shape of the glow, matches the predictions written in his equations a century ago. But much remains unknown. What lies within the event horizon, no science can yet uncover. Are intermediate mass black holes common, quietly lurking in star clusters, waiting to be revealed? Does the photon ring ripple with subtle distortions from quantum effects, hinting that the event horizon is not the end of physics, but the entrance to a deeper theory. In the decades ahead, more black hole images will come, sharper, finer, revealing not just their outlines, but the turbulence and heat of matter spiraling toward oblivion. Arrays in space will replace those on Earth. Gravitational waves will complement light, allowing us to not only see black holes, but to hear them. Between the ghostly intermediate mass black holes and the glowing photon rings of the giants, the universe sketches a portrait of gravity at its most extreme. Silent, invisible, merciless, yet beautiful in the way it shapes stars, clusters, galaxies, and light itself. In their darkness, black holes reveal the brightest truths about the structure of reality. At the heart of the Milky Way, far beyond the spiral arms and dust-veiled lanes of stars, lies a region of darkness and turbulence where ordinary physics begins to break down. It is a place hidden behind clouds of interstellar dust, invisible to the human eye, and yet it exerts a gravitational dominance over the entire galaxy. This is Sagittarius A, the supermassive black hole of our home galaxy, a silent anchor of 4 million solar masses, quietly shaping the motions of stars and the curvature of space around it. Sagittarius A is not a raging quasar like the black holes found in the hearts of young galaxies. It sits in a kind of cosmic restraint, consuming matter only in rare bursts, flickering briefly before sinking again into quiet. But although its appetite seems modest, its presence is unmistakable. Astronomers first suspected something was hiding in the constellation Sagittarius decades ago, long before they knew its nature. Deep radio observations in the 1950s revealed a compact bright radio source at the galaxy's center, yet nothing in visible light matched it. It was only by observing the stars around it that its true form was revealed. Beginning in the late 20th century, two teams, one led by Reinhard Genzel in Germany and the other by Andrea Ghez in the United States, spent decades tracking individual stars near the galactic core. They saw them race around an invisible point in tight, fast orbits, some completing a full revolution in less than 16 years at speeds of more than 5,000 kilometers per second. These were not random motions. They were planets circling an unseen sun. Only their sun was so small and heavy that nothing but a black hole could explain it. For this work, Ghez and Genzel were awarded the 2020 Nobel Prize in Physics. Through their observations, Sagittarius A ceased to be myth or theory and was established as a real, immense object from which not even light can escape. Unlike the luminous accretion disks seen in active galactic nuclei in other galaxies, Sagittarius A is starving. Little gas reaches it, and what does is too thin and hot to shine brightly before crossing the event horizon. Yet every so often, like the pulse of something half asleep, it flares. In X-rays and infrared, brief surges of brightness appear, possibly from small clumps of matter or asteroids being torn apart as they spiral in. Around it, a cluster of massive young stars circles in elegant, warped orbits, like moths spiraling toward an unseen flame. And deeper still, even closer to the point of no return, clouds of hot, magnetized plasma swirl in a silent hurricane, their radiation distorted by the warping of space and time. In 2022, the Event Horizon Telescope, a planet-sized network of synchronized radio observatories, produced the first image ever taken of Sagittarius A. It was faint and blurry, flickering by the minute, because the glowing plasma around it moved quickly. But it confirmed what Einstein predicted a century ago: a shadow, ringed by light bent around a black hole, caused by the photon orbit and the event horizon beyond which no information can return. This was humanity's first portrait of the dark heart of our own galaxy. If Sagittarius A is a quiet master of subtle gravity, its distant relative in the galaxy M87 is a titan who makes no effort to hide. 55 million light-years away, in the Virgo cluster, a monstrous black hole sits at the core of the giant elliptical galaxy Messier 87. It outweighs Sagittarius A by more than 1,000 times, containing 6.5 billion solar masses. Unlike the dormant center of our galaxy, M87 is active. It feeds on gas and dust, funneled toward it by the galaxy's vast gravitational well. This matter does not fall straight in. It spirals, forming a luminous accretion disk so hot that it emits X-rays. Magnetic fields twist and tangle around the spinning disk and black hole, and from the poles they launch a jet, a narrow, focused beam of plasma traveling at nearly the speed of light. This jet extends for thousands of light years into intergalactic space like a spear fired across the cosmos. M87's jet was first photographed in visible light by the Hubble Space Telescope. It glows with synchrotron radiation from electrons moving close to light speed along magnetic field lines. The jet's scale is staggering. If we could see it with the naked eye, it would stretch across the sky wider than the full moon, despite being tens of millions of light-years away. This jet is powered by the black hole's rotation, threading magnetic field lines through the event horizon like wires in a dynamo. Matter falls inward, but energy is launched outward, making the region around M87 one of the most violent in the known universe. In April 2019, the first direct image of a black hole ever produced by humanity was unveiled, and it was M87. The image showed a glowing, lopsided ring of radio light surrounding a dark, central void, the shadow of the black hole. That shadow matches precisely what general relativity predicts: a silhouette about 2.5 times larger than the event horizon itself, caused by light bending around the black hole. The brighter regions in the ring reveal where gas is moving toward us at relativistic speeds, beamed into our line of sight by the physics of special relativity. Time, space, and light intertwine to leave their mark in that blurry orange halo. Despite its size, M87 is easier to image than Sagittarius A. The black hole in our galaxy is closer but smaller, and its accretion flow changes rapidly over minutes. 87, being enormous, evolves slowly. Its gas takes days to orbit. This makes its image more stable, more photogenic. Yet both images of M87 and Sagittarius A confirmed the same truth. Black holes are not just theoretical curiosities. They are real. They obey Einstein's equations with exquisite precision, and they shape the galaxies that host them. The differences between these two black holes reflect two moods of the universe: one quiet, contemplative, pulling stars into invisible orbits; the other, loud, eruptive, launching matter toward the edge of intergalactic space. And yet, at their cores, they share the same essence: a place where gravity reigns supreme, time slows, matter is crushed beyond recognition, and light itself is bound to a final curve before surrendering to the void. Quasars are among the brightest beacons in the universe, yet their brilliance comes not from stars or supernova, but from matter falling into a supermassive black hole. At the core of certain galaxies, especially in the distant universe, the central black hole consumes gas and dust so rapidly that the infalling material heats to millions of degrees, releasing torrents of radiation across the electromagnetic spectrum. These objects are known as quasars, or quasi-stellar radio sources, because when first discovered in the mid-20th century, they appeared star-like through telescopes, mere points of light. Yet their spectra and radio emissions hinted at something far more powerful and very far away. The first quasar identified, 3C273, revealed an astonishing redshift, implying it was billions of light-years distant. For it to be so bright across such distances meant it emitted more energy every second than entire galaxies of hundreds of billions of stars. At the heart of a quasar lies a supermassive black hole surrounded by an accretion disk of swirling matter. Friction and magnetic turbulence within the disk heat it to such high temperatures that it glows in ultraviolet, optical, and X-ray light. Surrounding the disk is a thick torus of dust, which absorbs and re-radiates energy in the infrared. Fast-moving clouds of ionized gas orbit the black hole just beyond the disk, producing broad emission lines in quasar spectra due to gas moving at thousands of kilometers per second. Because of these broad lines and the extraordinary luminosity, quasars serve as lighthouses in the deep universe, illuminating the intergalactic medium and tracing the history of structure formation. Quasars were most common when the universe was young, particularly around 10 to 12 billion years ago, during what astronomers call the Quasar epoch. Galaxies in that era were rich with cold gas, ideal fuel for black holes. As black holes devoured matter, they grew rapidly, sometimes reaching billions of solar masses within a few 100 million years of the Big Bang. This raises one of cosmology's greatest questions. How did black holes grow so big so fast? Some theories suggest they formed from the direct collapse of enormous primordial gas clouds. Others propose they are built up from countless mergers of smaller black holes. Whatever their origin, quasars became engines of transformation, blowing fierce winds and launching jets of plasma that could sweep away gas from their host galaxies, shutting down star formation. In this way, they helped shape galaxy evolution itself. Sometimes, the universe provides the perfect alignment of light, gravity, and distance to turn these brilliant objects into even more spectacular phenomena. When a quasar lies far behind a massive galaxy or cluster of galaxies, the light from the quasar can be warped, magnified, or even duplicated by the intense gravity of the intervening mass. This effect, known as gravitational lensing, was predicted by Einstein's theory of general relativity, but not observed until decades later. A massive object bends the fabric of space-time, and light traveling near it follows that curve, creating multiple paths from the quasar to Earth. As a result, we might see several images of the same quasar, arranged in arcs, rings, or crosses. These are called lensed quasar systems. One of the most famous is the Einstein cross, officially known as Q2237+0305, where 4 images of a single quasar appear around the foreground galaxy's core like points of a celestial compass. Another is the twin quasar, Q0957+561, whose two images allowed astronomers to measure the time delay between brightness variations in each image, giving one of the first calculations of the Hubble constant, the rate at which the universe expands. In some rare cases, if alignment is nearly perfect, the quasar's light can form a complete circle around the lensing galaxy, known as an Einstein ring. Lensed quasar systems are more than visual curiosities. They are tools that let us study dark matter, the invisible substance that makes up most of the universe's mass. Small clumps of dark matter within the lensing galaxy can subtly distort the quasar's images, changing their brightness or shape. By measuring these changes, astronomers can infer the distribution of dark matter, something otherwise completely invisible. Lensed quasars also allow precise measurements of cosmic expansion through a technique called time delay cosmography. When the quasar varies in brightness, we see the changes arrive in each image at different times because the light paths are different lengths. Measuring these delays allows us to calculate cosmological distances with remarkable accuracy. Even the quasar's own light tells a story as it travels through space. It passes through gas clouds between galaxies, each leaving tiny absorption fingerprints. By studying these absorption lines, astronomers map the cosmic web, the grand network of filaments, clusters, and voids formed by gravity pulling matter through billions of years. Some of the most distant quasars known, seen as they were less than 1 billion years after the Big Bang, show us the universe transitioning from darkness into light during the epoch of rionization. Before stars and galaxies lit up, the universe was filled with neutral hydrogen gas. The light from early quasars pierced this fog, ionizing gas and revealing the first large-scale structures. Closer to home, within the structure of a quasar itself, lies a complex ecosystem of gas, dust, and magnetic fields. Many quasars launch jets from their poles, narrow beams of charged particles accelerated to near light speed by magnetic fields twisted around the black hole's spin. These jets can extend hundreds of thousands of light years, shining in radio wavelengths and creating lobes of accelerated plasma. These are seen in radio galaxies and in quasars viewed at certain angles. Jets and quasar winds can heat or expel gas from their hosts, regulating growth and leaving vast bubbles in intergalactic space. Despite their distant origin, the light we capture from quasars today began its journey billions of years ago. Some quasars seen by modern telescopes started shining when Earth had no life, no oceans, perhaps not even continents. They have burned across the universe's history, leaving cosmic archaeologists with records of the early universe, the birth of galaxies, and the rise of black holes. In the rarest and most beautiful of cases, gravity transforms their light into something even more poetic. A quasar's rays, curved by intervening galaxies, form arcs, crosses, or circles, cosmic mirages written in light and space-time. These lensed quasars are not separate objects, but duplicates of a single source, delayed echoes of the same event. When the quasar brightens, each image brightens in turn, separated by days or weeks. To study one is to study time itself, captured along multiple paths through the universe's invisible architecture. Quasars are not merely distant points of light. They are engines, fossils, laboratories, and lanterns through which the universe reveals its deepest structures. And when gravity bends their light just so, they become even more valuable. Magnified voices from across time, helping us measure the cosmos, weigh invisible matter, and trace the fabric of space-time itself. They are among the most ferocious beacons in the universe, not because they are the largest, or the most massive objects in existence, but because of the direction they face. A blazar is a quasar turned directly toward us. A galaxy whose central supermassive black hole launches a jet of matter and radiation so precisely aligned with Earth that we are caught in the full brilliance of its beam. These objects are not gentle cosmic lighthouses. They are particle cannons, powered by superheated plasma, spiraling into a black hole, compressed and twisted by magnetic fields until they erupt outward at nearly the speed of light. If most quasars are grand fires seen from afar, a blazar is the fire pointed straight at the observer. The heart of a blazar is still a supermassive black hole, often between 100 million and several billion times the mass of the Sun. Surrounding it is the familiar accretion disk of gas, dust, and stellar debris heated to incandescent temperature as it falls inward. But not all of that matter reaches the event horizon. Some is trapped in magnetic field lines that thread through the disk, and black holes spin, accelerating electrons and protons to energies so intense they escape along the poles in thin, focused jets. When one of those jets is aimed toward Earth, relativistic effects amplify its brightness. Radiation that would be modest if seen from the side becomes violent and variable, flickering in minutes or hours. To telescopes, they appear capable of shifting in brightness in the time it takes to drink a cup of coffee. Blazars emit energy across the entire electromagnetic spectrum. In radio waves, they are steady, powerful sources. In optical light, they can flare unpredictably. In X-rays and gamma rays, they are among the brightest objects in the universe. On rare occasions, blazars become so active that they are visible to amateur telescopes, appearing as a faint star in the sky. But stars do not dim and rise in brightness by factors of 10 overnight. The first blazar ever identified, BL Lacerti, was mistaken for a star until its spectrum revealed no absorption lines characteristic of stellar atmospheres. Instead, it glowed with the smooth, featureless continuum of synchrotron radiation, light emitted by charged particles spiraling along magnetic fields at relativistic speeds. Blazars belong to a broader class called active galactic nuclei, but they are the most extreme. Some are classified as BL-LAC objects, with almost no emission lines, suggesting their jets dominate the light we see. Others, known as flat-spectrum radio quasars, show stronger emission lines and more powerful accretion disks. Both are thought to be the same kind of object viewed from slightly different angles. In their host galaxies, which are often giant ellipticals, stars and gas move in quiet patterns, but at their cores, space is being twisted, matter shredded, and energy converted directly from gravity into light. The power of blazars is not only in their brightness, but in their use as tools. When high-energy photons from a blazar collide with extragalactic background light, they annihilate into electron-positron pairs. By studying how much blazar light is absorbed on its journey to Earth, scientists can measure the density of background radiation across the universe, light from every star that has ever burned. Blazars also emit neutrinos, ghostly particles that rarely interact with matter. In 2017, a neutrino detected by the Ice Cube Observatory in Antarctica was traced back to a blazar called TXS 0506-056. It was the first time an individual source was identified as producing both light and neutrinos, revealing blazars as cosmic accelerators capable of forging the highest energy particles in nature. Yet not all active galactic nuclei shout like blazars. Some whisper. In the hearts of many spiral galaxies, including galaxies much like our own, lie Seyfert nuclei, active black hole systems less luminous than quasars but closer to home and more numerous. First identified in the 1940s by the astronomer Carl Seyfert, these galaxies appear normal in visible light but have unusually bright cores with strong emission lines from highly ionized gas. Seyfert galaxies are categorized into two major types. Type 1 Seyferts show both broad and narrow emission lines, indicating gas orbiting close to the black hole at immense speeds, as well as slower-moving gas farther out. Type 2 Seyferts show only narrow lines, suggesting that the more turbulent inner regions are hidden from direct view. The difference between these types is not believed to be intrinsic. Instead, it appears to be a matter of perspective. According to the unification model of active galaxies, all AGN have the same basic structure: a central black hole, an accretion disk, fast-moving gas in a broad line region, slower gas in a narrow line region, and a thick torus of dust and gas wrapped around the center. If we view the galaxy at an angle where the torus blocks our line of sight to the inner regions, we see a Type 2 Seyfert, its broad line region hidden, only the narrow lines visible. If we view it more face-on, unobscured, we see a Type 1 Seyfert, with both line regions visible. Seyfert galaxies may not have the dramatic jets of blazars or the overwhelming luminosity of quasars, but they are essential to understanding how black holes and galaxies evolve together. The black holes at their centers typically weigh millions of solar masses, comparable to Sagittarius A, and feed more gently than the ravenous quasars of the distant universe. The radiation from Seyfert nuclei ionizes gas far beyond the core, creating emission line nebulae that can stretch for thousands of light years. In some, faint jets or outflows can be seen, but they are weaker, less focused than blazar jets. They are, in a sense, a quieter phase in the life cycle of an active galaxy. Perhaps they are quasars that have run out of gas, fading into dormancy. Or perhaps they are black holes that never fed enough to become quasars in the first place. Their variability can be rapid, with brightness changing over days or hours, a sign that the emitting regions are compact, no larger than our solar system. Their spectral fingerprints show heavy elements forged in earlier generations of stars, heated to tens of thousands of degrees. Blazars and Seyfert galaxies are two moods of the same cosmic engine, an active black hole. When its jet is pointed at us, it becomes a blazar, fierce and unpredictable, a flashlight of the gods aimed at Earth. When seen from the side, through veils of dust and ionized gas, it is a Seyfert galaxy, more modest, its violence half hidden. Both are governed by rotation, magnetism, and gravity. Both feed on the same raw material, cold gas drawn inward from the galaxy around them. One shouts, the other speaks in breathless whispers. But in both, we witness the same truth, that galaxies are not entirely serene, that their centers can blaze with the energy of annihilated matter, and that within those hearts, black holes do more than swallow light. They shape the fate of the galaxies that give them life. There are objects in the universe that shine so intensely in X-rays that they appear to defy our understanding of what compact objects should be capable of. These are the ultra-luminous X-ray sources, or ULXs, cosmic power stations that radiate more X-ray energy than an entire galaxy of normal stars combined. They are not located at galactic centers, and they are not supermassive black holes. Instead, they dwell in the outer arms of galaxies, among regions of star formation or ancient clusters, producing X-ray luminosities 100 to 1,000 times higher than what a stellar mass black hole should be able to emit. For years, astronomers argued about their true identity. Were they intermediate mass black holes, quietly feeding? Or were they stellar remnants, somehow breaking the Eddington limit, the point at which radiation pressure should blow away infalling matter and halt further accretion? As telescopes improved, the mystery deepened. NASA's Chandra X-ray Observatory, ESA's XMM Newton, and Japan's Suzaku Observatory collected spectra, light curves, and pulsations from ULXs across many galaxies: M82, the Whirlpool Galaxy, Centaurus A. Some ULXs flickered, others pulsed, some launched jets, and some glowed steadily. In 2014, a breakthrough arrived with the discovery of M82X2, a ULX exhibiting regular pulsations, clear evidence of a neutron star. A neutron star, only 20 kilometers across, was emitting more than 100 times the Eddington luminosity expected for such an object. This overturned previous assumptions. ULXs weren't just black holes, they could be neutron stars with magnetic fields so strong that they funneled accretion onto their poles, allowing matter to fall without being blown away. These ultra-luminous X-ray pulsars are extreme versions of X-ray binaries, swallowing gas from a companion star with insatiable hunger. Other ULXs may still hide intermediate mass black holes, but the growing evidence shows that many are simply stellar remnants being pushed to their physical limits. In some, the accretion disk is so thick that radiation escapes in narrow beams, making them appear brighter from our angle, an effect known as geometric beaming. In others, magnetic fields suppress radiation pressure in specific directions. ULXs are not impossible anomalies. They are demonstrations of nature's ability to take known physics, gravity, magnetism, nuclear density, and stretch them to their edge. To understand ULXs better, one must first understand X-ray binaries, the broader family to which they belong. An X-ray binary is a star system with two members: a compact object, either a neutron star or a black hole, and a companion star transferring mass. That infalling matter forms a disk around the compact object, heating through friction to millions of degrees and emitting X-rays. X-ray binaries are divided into two types based on the companion star. High-mass X-ray binaries, or HMXBs, have young, massive companions, O or B-type stars, often dozens of times the Sun's mass. These systems form in star-forming regions, and the massive companion star drives strong stellar winds. The neutron star, or black hole, captures part of this wind, creating a steady stream of accreting matter. HMXBs can be dramatic, with intense variability and powerful outbursts. Because the massive star will eventually go supernova, many HMXBs are short-lived on cosmic timescales, lasting only a few million years. Low-mass X-ray binaries, or LMXBs, have smaller, older companion stars, like the Sun, or smaller, transferring matter through Roche lobe overflow. In these systems, the companion has swollen enough that its surface spills material gravitationally toward the compact object, forming an accretion disk that glows in X-rays. LMXBs are often found in older stellar populations, including globular clusters and galactic bulges. They can remain stable for billions of years, quietly feeding their compact objects. Unlike HMXBs, their X-ray emission is smoother, more periodic, and often shows quasi-periodic oscillations, subtle vibrations that reveal details about the innermost disk close to the event horizon or neutron star surface. Both kinds of X-ray binaries are laboratories for understanding extreme physics. In HMXBs, like Cygnus X1, one of the first black hole candidates ever discovered, the compact object continuously siphons material from a blue supergiant star. In LMXBs, like Scorpius X1, the brightest persistent X-ray source in the sky after the Sun, a neutron star devours a modest companion star with terrifying efficiency. Some systems flip from quiet to violent states without warning, releasing bursts of X-rays called Type I X-ray bursts, thermonuclear explosions on the surface of accreting neutron stars. Their light curves are not random noise. They contain patterns, oscillations, harmonics, telling astronomers about the physics of matter just before it crosses the brink of a black hole or is crushed onto the surface of a neutron star. In black hole binaries, the inner edge of the accretion disk may approach the event horizon, allowing measurements that test general relativity in its strongest form. In neutron star binaries, accretion onto a solid surface and the presence of intense magnetic fields create pulsars, millisecond signals that sweep across space like cosmic metronomes. Some X-ray binaries evolve into ULXs when accretion rates exceed the ordinary limits. Others die quietly, their fuel exhausted, leaving behind dormant black holes or recycled millisecond pulses. In rare cases, mass transfer becomes unstable, leading to a merger, creating a kilonova, a burst of gravitational waves, and sometimes a short gamma-ray burst. These are the systems that forge gold, platinum, and other heavy elements, seeding galaxies with the building blocks of planets. ULXs and X-ray binaries are two faces of the same story: matter falling into the darkest objects in the universe. In one, the process is modest: steady accretion, bright X-rays, stable orbits. In the other, accretion becomes extreme, breaking normal limits, beaming light in fierce torrents. Both teach us that death in the universe is not silent. When a star collapses into a neutron star or black hole, it does not simply vanish. It enters a new relationship with a companion star, with gravity, with magnetism, and begins shining again, not with fusion, but with the energy of matter being consumed. In the end, ULXs are the loudest voices in a quiet but powerful symphony played by X-ray binaries across the universe. They show us how far nature can push an accreting star before breaking it. They reveal neutron stars masquerading as giants, black holes devouring faster than theory once allowed, and perhaps, in some rare systems, the missing intermediate mass black holes we have sought for so long. Through them, we glimpse how gravity and matter write their final conversations in X-rays before fading into silence. They are small in size, but colossal in power, scaled-down versions of the most energetic engines in the universe. Microquasars, as their name suggests, are miniature analogues of quasars. Where quasars are powered by supermassive black holes millions or billions of times the mass of the Sun, microquasars arise from stellar remnants, black holes or neutron stars a few times the Sun's mass, feeding on a nearby companion star. Despite the difference in scale, the physics is strikingly similar. A companion star loses matter, either gently through stellar winds or violently through Roche lobe overflow. That matter spirals inward, forming a hot accretion disk around the compact object. Magnetic fields twist and channel part of the falling gas into jets that fire outward at nearly the speed of light. Like quasars, microquasars unleash radiation across the electromagnetic spectrum, from radio waves to X-rays. But while quasars evolve over millennia, microquasars can change dramatically in a single day. They are the fast-forward version of cosmic jet engines. One of the first discovered, and still one of the most famous, is SS 433, located in the constellation Aquila. This system astonished astronomers when they first noticed that its emission lines were steadily shifting in wavelength, moving back and forth. This was caused by its twin jets precessing, slowly changing direction like a spinning top, shooting out material at a quarter of the speed of light. These jets contain baryonic matter, protons and neutrons, unlike the electron-positron jets believed to dominate in quasars. Other microquasars, such as GRS 1915-105, exhibit near-relativistic jets and dramatic variability in X-ray brightness, sometimes flaring dozens of times in a single hour as the inner accretion disk becomes unstable, empties, reforms, and launches new jets. Microquasars are valuable precisely because they operate on human timescales. The processes that power AGN jets in distant galaxies occur over tens of thousands of years, but in microquasars, the same mechanisms unfold within hours or days. This allows astronomers to study how jets form, how magnetic fields extract rotational energy from the accretion disk or compact object, and how matter behaves in the grip of extreme gravity. Their X-ray emissions track the structure of the accretion disk, while radio waves trace the jets racing into space. Some microquasars even emit gamma rays and possibly neutrinos, making them miniature laboratory for the most exotic physics the universe can offer. They are also violent sculptors of their environment. In some microquasars, jets plow into surrounding gas clouds, carving out cavities and leaving behind synchrotron-emitting lobes like cosmic footprints. This mirrors the vast radio lobes seen around galaxies with active nuclei, but on a scale measured in light-years instead of millions of light-years. The connection between the two classes, quasars and microquasars, suggests that black holes follow similar rules regardless of size. Only the scale changes, not the nature of the engine. Yet microquasars would not exist without a more ancient and foundational catastrophe, a supernova. Specifically, a core collapse supernova, the death cry of a massive star. When a star more than 8 times the mass of the Sun exhausts its nuclear fuel, fusion in its core ceases. Without radiation pressure to counterbalance gravity, the core collapses within a fraction of a second. Protons and electrons are crushed into neutrons, and the core becomes an ultra-dense neutron star, or, if massive enough, collapses further into a black hole. The infalling outer layers slam into this sudden, rigid core and rebound, triggering a monstrous shockwave. Neutrinos, ghost-like particles produced in the dense core, flood outward by the trillions, depositing energy into the stalled shockwave and reviving it. The star detonates, blowing off its outer layers into space. For a few weeks, it outshines entire galaxies. Core collapse supernovae come in several varieties, classified by whether hydrogen or helium is present in their spectra. Type-O supernovae retain hydrogen in their outer envelopes, while types Ib and Is have lost theirs, stripped either by stellar winds or binary companions. Despite these differences, the underlying mechanism remains the same. The iron core collapses and the star explodes. The remains of this explosion scatter heavy elements: oxygen, silicon, sulfur, calcium, iron into space, seeding future stars, planets, and life. Every atom of iron in human blood, every atom of calcium in bones, every oxygen atom we breathe was born long ago in the heart of a dying star and flung into the universe by a supernova. Sometimes the explosion is not powerful enough to blow everything away. The core collapses into a black hole, and the explosion falters, causing the outer layers to fall back, feeding the black hole and birthing a microquasar or a gamma-ray burst. In extreme cases, the stellar collapse channels its energy into a pair of relativistic jets that bore through the star's poles and erupt as a long gamma-ray burst. Another class already explored earlier in this book. But in most cases, a neutron star remains, spinning rapidly, generating powerful magnetic fields. This newborn neutron star may later become a pulsar or, with a close companion star, the engine of a microquasar. The remnants of core collapse supernovae. The supernova remnants are ethereal structures of gas and dust expanding through space. The Crab Nebula, born from a supernova seen by Chinese astronomers in 1054, is one such remnant. At its center lies a rapidly spinning neutron star, a pulsar, beaming radio waves and particles into space. Its filaments glow in red hydrogen light, green oxygen emission, and blue synchrotron radiation from high-energy electrons. Cassiopeia A, another remnant, expands like a cosmic bruise, its shock waves still plowing into interstellar gas. These remnants carry within them the fingerprints of the elements forged in the explosion, allowing astronomers to reconstruct the star's life and death. Without core collapse supernovae, galaxies would be cold and lifeless, their gas locked in stars with no way to recycle. Supernova shockwaves compress nearby clouds of hydrogen, triggering new star formation. Their heavy elements enrich those newborn stars with the ingredients for planets. Their neutron stars and black holes become the engines of X-ray binaries, pulsars, microquasars, and gravitational wave events. In death, massive stars give birth to some of the universe's most energetic phenomena. Thus, the story of microquasars is inseparable from the story of supernovae. One is the silent devouring that follows. The other is the cataclysmic birth of silence. A star dies in fire, leaves behind a collapsed heart. Then, if fate grants it a companion, that heart feeds and roars back into light, launching jets into the void. Across the universe, binary stars continue their ancient dance until gravity, rotation, and time bring them to this final crescendo. One becomes a corpse, the other a donor, and together they ignite again, not as a star, but as a jet, screaming into the dark. There are stars that do not die quietly or even collapse under their own weight, but instead obliterate themselves entirely in thermonuclear fury. Unlike the core collapse supernovae that mark the deaths of massive stars, Type Ia supernovae are the spectacular ends of smaller, denser stars, white dwarfs. These white dwarfs are the crystalline corpses of stars like our Sun, no longer generating energy through fusion, sustained only by the quantum pressure of electrons. They drift silently in space, cooling slowly over billions of years, unless fate binds them into a binary system. When a white dwarf orbits closely with another star, it can begin to steal matter from its companion. Minute by minute, hydrogen or helium streams across the gravitational bridge between them, collecting on the dwarf's surface. It gains weight. The pressure in its core rises, and when it approaches approximately 1.4 times the mass of the Sun, the Chandrasekhar limit, the balance of forces collapses. At this moment, the temperature and pressure in the white dwarf's heart reach levels high enough to ignite carbon fusion. But unlike normal stars, where fusion proceeds steadily, the white dwarf has no room to expand and regulate the burn. So the fusion spreads like wildfire across its surface and then detonates inward. In less than a second, the entire star undergoes runaway thermonuclear combustion. Carbon and oxygen turn into nickel and iron in an explosion so symmetrical and so complete that the white dwarf is vaporized. Nothing remains. No core, no remnant, no neutron star or black hole. Just a rapidly expanding shell of glowing gas flying outward at tens of thousands of kilometers per second. Because this process always occurs at nearly the same mass and under nearly the same conditions, type I supernovae explode with an almost identical intrinsic brightness. This makes them cosmic distance markers, standard candles. In the 1990s, two teams measuring distant type Ia supernovae discovered to their astonishment that the universe is not just expanding, it is accelerating. Some unknown energy permeating the cosmos was pushing galaxies apart faster and faster. This was the first direct evidence for dark energy, a force that now dominates the universe and shapes its destiny. The humble white dwarf, long dead and invisible, became the key to understanding the fate of all things. But not all stellar deaths follow the quiet path to a white dwarf or the iron core collapse to a neutron star. Some stars, far larger than any known in the modern universe, meet yet another fate, the pair instability supernova. These stars are cosmic giants, born with masses between roughly 100 and 250 times that of the Sun, and their cores grow so hot, over 1 billion degrees, that gamma-ray photons fill their interiors like a blinding storm of light. Under these temperatures, gamma photons have enough energy to spontaneously transform into matter electron-positron pairs. When this occurs, radiation pressure, which normally supports the star against gravity, suddenly decreases. The core loses its strength. It contracts, and in that instant of collapse, oxygen and silicon within the core ignite in a thermonuclear explosion that does not merely blow off the outer layers. It tears the entire star apart from the inside out. Unlike core collapse supernovae, pair instability events leave no remnant behind. There is no black hole, no neutron star, only an expanding cloud of heavy elements seeding the galaxy. If the star is slightly less massive, around 70 to 120 solar masses, it may undergo pulsational pair instability, where the core partially collapses and explodes, but not completely. It loses mass in violent pulses, expelling shells of gas into space. This can repeat several times until the final collapse produces either a true pair instability explosion or a black hole. Stars above around 250 solar masses may bypass explosion entirely and collapse directly into black holes, perhaps the seeds of the first supermassive black holes found in early galaxies. Pair instability supernovae are believed to have been common in the very early universe, when the first stars, so-called population 3 stars, formed from pristine hydrogen and helium left over from the Big Bang. Without heavier elements to cool the gas, these stars grew to colossal sizes. When they died, they may have exploded in pair instability supernovae, enriching the young universe with the first iron, carbon, oxygen, and silicon. These explosions would have been far brighter than most modern supernova, glowing for months, visible across the infant cosmos. They were the universe's first alchemists. Modern telescopes are now scanning distant galaxies for the signatures of these ancient giants. The James Webb Space Telescope has already observed extremely luminous supernovae in galaxies formed when the universe was less than 500 million years old, events that may be pair instability explosions. Their light curves linger longer and brighter than Type II supernovae. Their spectra are rich in elements like oxygen and magnesium but show no traces of hydrogen. Some known superluminous supernovae in the contemporary universe might also be examples of pair instability events in metal-poor galaxies, where massive stars still form. Type Ia supernovae and pair instability supernovae could not be more different in origin, yet they are bound by a shared truth. Both are thermonuclear catastrophes. One is the death of a small star's corpse, the other the death of a cosmic titan. One results from accumulated ashes of a companion's life, the other from the internal collapse of a primordial furnace. One is used to measure the size of the universe. The other may explain how it became chemically rich. And while a Type Ia supernova leaves nothing but gas and memory, a pair instability supernova leaves the same, yet on a grander scale with heavier elements and a longer echo. Both are acts of unbinding. In one, gravity binds a white dwarf so tightly that only fusion can tear it apart. In the other, radiation supports a star so large that only the creation of matter from light can undermine it. Both speak of thresholds, the Chandrasekhar limit, beyond which a white dwarf must explode, the Eddington luminosity, past which radiation pressure pushes back against gravity, the temperature at which gamma rays turn into matter, the point where stars stop living and start falling apart. Supernovae are not just the deaths of stars, they are the creators of everything solid. The iron at the core of Earth, the silicon in rocks, the calcium in bones, the carbon in trees, the oxygen we breathe, all forged in supernovae. Every explosion, whether a modest Type Ia or a colossal pair instability, is an act of creation delivered by destruction. The silence that follows their blinding light is the silence of a universe richer than before. When stars live and die, most follow one of a few well-known paths. Ordinary stars, like the Sun, become white dwarfs, and massive ones collapse in core collapse supernovae, leaving behind neutron stars or black holes. But nature, as always, hides exceptions, rare, transitional fates that occur only under very specific conditions. Among these are electron capture supernovae, explosions too weak to be classical supernovae and yet too violent to be quiet endings, and failed supernovae, where stars collapse directly into black holes without ever exploding. These are not the famous deaths of the brightest stars, they are the quiet tragedies and forgotten endings of stellar evolution, and they reveal how precarious the balance of matter, energy, and gravity truly is. An electron capture supernova begins not with a colossal star of 20 or more solar masses, but with one more modest, between about 8 and 10 times the mass of our Sun. These stars spend millions of years fusing hydrogen into helium, then helium into carbon and oxygen, as many stars do. But unlike truly massive stars, they do not reach the temperatures required to fuse carbon completely into heavier elements. Instead, their cores grow into a curious composition, a mixture of oxygen, neon, and magnesium. Around them, layers of helium and hydrogen still burn, slowly feeding mass into the core. Over time, the core grows denser, its atoms more tightly packed, until the intense gravity begins crushing electrons into atomic nuclei. Normally, electron degeneracy pressure, an invisible quantum force, holds the core up, resisting collapse. But in these stars, as density rises past a critical point, the nuclei of magnesium and neon begin capturing free electrons. Protons within those nuclei turn into neutrons, creating heavier, neutron-rich atoms. This electron capture process strips away the very pressure keeping the core stable. Suddenly, the star's last defense against gravity is gone. The core collapses in a fraction of a second. The outer layers crash inward, rebound off the newly formed neutron core, and an explosion blossoms outward. But unlike the intense brilliance of classic core collapse supernovae, this explosion is faint, almost reluctant. It produces less radioactive nickel-56, the element that powers the bright afterglow of other supernovae. The light curve is dimmer, the expelled mass lower, the energy only a fraction of what a true massive star explosion would release. Astronomers believe some historical supernovae, such as SN 1054, the one that created the Crab Nebula, were electron capture events. The light lasted weeks, but was not overly bright, and the remnant was a neutron star, not a black hole. These supernovae occupy a kind of liminal space in stellar death, too massive to remain white dwarfs, too small to burn heavy elements into iron, destined instead to collapse as soon as quantum pressure itself is undermined. The stars that produce these explosions are rare, forming only in a narrow mass range. Yet they are vitally important, helping seed galaxies with elements like oxygen and neon, and providing one of the pathways by which neutron stars are born. But sometimes, a star does not explode at all. There are stars so heavy that when their cores collapse, no shockwave is able to force the outer layers back out. These stars, red supergiants or blue hypergiants, tens of times more massive than the Sun, reach the end of their nuclear life and begin the same collapse that triggers normal supernovae. The core collapses into a neutron star or black hole, and a shockwave forms. But in these rare cases, the shockwave stalls and never recovers. Neutrinos, normally responsible for reviving the explosion by heating the gas, escape without transferring enough energy. The star's core, now a black hole, exerts such immense gravity that the collapsing material never finds the strength to escape. The star simply vanishes. Its outer layers fall inward, swallowed silently. No bright supernova lights the sky. No neutron star emerges. Only darkness remains. This is a failed supernova, a direct collapse. For centuries, astronomers believed all massive stars ended their lives in supernova explosions. That belief began to change in the early 2000s when surveys observed massive stars that simply disappeared. One famous case is a star in the galaxy NGC 6946, catalogued as N6946 BH1. It was a red supergiant, 25 times the mass of the Sun. In 2009, it grew slightly brighter, as though preparing for a supernova. But then, it faded and was gone. No explosion followed. Infrared observations revealed only a faint afterglow, consistent with dust, heated by material falling into a newborn black hole. The star had not exploded. It had collapsed directly. Failed supernova may be common. Some models suggest that up to 10%, 30% of massive stars die this way. If so, the universe is filled with black holes born in complete silence. These collapses may even be responsible for some of the most massive stellar black holes detected through gravitational waves, objects weighing 30, 40, even 60 times the mass of the Sun. In failed supernovae, nearly all of the star's mass falls inward rather than being blasted into space. These direct collapse black holes may also explain why some galaxies have fewer supernova remnants than expected, and why some elements are less abundant in certain regions, because those stars never enriched space with their ashes. While electron capture supernovae and failed supernovae may seem like opposites, one a subtle explosion, the other a complete absence of one, they are connected by a deeper truth. Not every star follows the heroic script of bright death and cosmic fireworks. Some stars die in confusion, neither fully explosive nor peacefully fading. Some collapse because electrons are eaten by their own nuclei. Others because gravity overwhelms every force, every photon, every neutrino. The universe does not demand symmetry. It only follows its laws, indifferent to the spectacle. In these lesser-known endings, we glimpse the quiet machinery of existence. A star of 9 suns, carbon burning but not hot enough to forge iron, waits until quantum pressure fails and detonates in modest light. A star of 30 suns, its core forming iron, collapses. Yet the shock never rises, and the night remains dark. In one case, a neutron star is born. In the other, a black hole appears with no announcement. These events shape galaxies in unseen ways. Electron capture supernovae produce neutron stars found in ancient clusters. Failed supernovae create black holes so heavy they need no mergers to grow. Their births echo faintly in gravitational waves, alter the distribution of elements, and solve long-standing mysteries about missing explosions and missing masses. And so, between the bright and the silent, the universe weaves this tapestry. Not all stars die with glory. Not all deaths are seen. But each has its place in the grand design, where gravity, pressure, and light wrestle for a final time, and a star either speaks its last breath to the cosmos or sinks away without a sound. When a massive star dies in a supernova, the explosion itself burns only for a fleeting moment in cosmic time. What remains is something quieter, but no less extraordinary: a supernova remnant, the expanding corpse of a once mighty star. These remnants are not just debris drifting in space. They are the forges that blend, scatter, and recycle the universe's elements. Born from chaos, they drift through the galaxy like ancient ghosts, shells of gas, dust, and shockwaves that continue shaping the cosmos long after their parent star has died. They are the fingerprints of stellar death, written in filaments of oxygen, nitrogen, iron, and carbon, glowing under starlight and bathed in radiation. A supernova remnant begins the moment the explosion's shockwave tears through the star's outer layers and hurls them into space at thousands of kilometers per second. This shockwave slams into the surrounding interstellar medium, compressing it, heating it, lighting it up in X-rays and radio waves. As it expands, it sweeps up material like a broom across a dusty floor, carving cavities in gas clouds and triggering the birth of new stars. The remnant evolves through stages. First, the free expansion phase, when the ejected material moves almost unimpeded. Then the Sedov-Taylor phase, when swept-up matter slows the blast and the remnant forms a hot, pressurized bubble. And finally, the radiative phase, when the gas cools and condenses into intricate tendrils and knots. Some remnants are spherical and symmetrical, neat, like soap bubbles. Others twist into shapes sculpted by magnetic fields, stellar winds, or dense clouds. The Crab Nebula, perhaps the most famous remnant, lies in the constellation Taurus. Born from a supernova witnessed in 1054 by Chinese astronomers, its filaments glow in red hydrogen light, green oxygen emission, and a haunting blue haze of synchrotron radiation. At its heart spins a neutron star, the Crab Pulsar, rotating 30 times per second, spewing beams of radiation and winds of charged particles that carve and energize the nebula around it. Cassiopeia, another spectacular remnant, reveals expanding shells and knots of calcium, iron, and sulfur. It is only about 350 years old, yet already spans 30 light years, expanding into space like a silent, unstoppable hurricane. Supernova remnants are laboratories of high-energy physics. Within their shock fronts, particles are accelerated to nearly the speed of light, becoming cosmic rays that eventually travel across the galaxy and sometimes strike Earth's atmosphere. These shocks, powered by magnetic turbulence, are nature's particle accelerators, far surpassing anything humans have built. Remnants also generate complex molecules and dust grains. Although supernovae can destroy dust, they also forge it in vast quantities. Remnants like SN 1987A show rings of freshly minted dust glowing in the infrared. As beautiful as supernova remnants are, they are only one side of a deeper story. The explosion that births them is not driven primarily by light or heat, but by something far more elusive: neutrinos. These ghost-like particles carry away most of the energy of a collapsing star, and without them, even the brightest supernova would never occur. When the core of a massive star collapses, forming a neutron star, the density becomes so great that protons and electrons merge into neutrons, releasing a flood of neutrinos. In just 10 seconds, the core emits more energy in neutrinos than all the stars in the universe emit in light during the same time. These neutrinos interact so weakly with matter that almost all of them escape the star freely. Only a tiny fraction collide with the dense stellar material, depositing enough energy to revive the stalled shockwave and drive the explosion outward. Without this brief but critical neutrino heating, the shock would collapse back inward, and the star would implode into a black hole in silence. Thus, the visible explosion we call a supernova is paradoxically the faintest part of the event's energy release. The true force lies in the invisible burst of neutrinos that precedes the explosion by a heartbeat. For millennia, neutrino bursts remained theoretical, proposed by physicists as the missing link between core collapse and the outward blast. Proof finally arrived in 1987, when a supernova erupted in the Large Magellanic Cloud, a neighboring dwarf galaxy about 168,000 light-years away. This was supernova 1987A, the nearest observed supernova since the invention of the telescope. In the hours before the light of the explosion reached Earth, neutrino detectors deep underground, Kamiokande 2 in Japan, IMB in the United States, and Baksan in Russia recorded a handful of neutrinos arriving from the direction of the Large Magellanic Cloud. Only 24 neutrinos were detected across the world, yet those few silent messengers confirmed a theory decades in the making. Supernovae announce themselves in neutrinos before they do in light. Those neutrinos traveled freely through the collapsing star and across space, reaching Earth before the light burst through the outer layers. They also confirmed that the collapsed core became a neutron star. Ever since, neutrino observatories have been listening to the star's final whispers. The next time a supernova erupts in the Milky Way, thousands of neutrinos will arrive in detectors like Super Kamiokande, Ice Cube in Antarctica, Juno in China, and June in the United States. These neutrinos will tell us the details of the collapse, the formation of the neutron star or black hole, and the conditions deep in the core, information no telescope can ever see. Neutrinos are almost untouchable. Billions pass through every square centimeter of your body every second, streaming from the sun, from cosmic rays, from nuclear reactors, and from ancient supernovae. Yet they rarely interact. This property makes them perfect messengers. Unhindered by gas, dust, or magnetic fields, they carry information from the innermost moments of stellar death to the outer edges of the universe. Some have traveled since seconds after the Big Bang. Others were born in galaxies we have not yet discovered. But in core collapse supernovae, neutrinos are not merely witnesses. They are the architects of destruction and rebirth. Supernova remnants and neutrino bursts represent two different ways of hearing a star's death. One is seen in luminous clouds stretching across light years, glowing in colors no eye can see. The other is silent, invisible, buried in numbers, appearing on a detector screen in a laboratory miles underground. Yet both are part of the same story, the transformation of a star into either a neutron star, black hole, or dust. One is the visible echo, the memory etched across space. The other is the heartbeat, the instant of collapse and rebirth. From a distance, a supernova remnant is a painting, a delicate lace of gas drifting among the stars. Up close, it is a storm of shock waves, magnetic vortices, and particles accelerated to near light speed. Somewhere inside it, a neutron star pulses, or a black hole swallows in silence. And just at the moment of its birth, before any light escapes, a storm of neutrinos carries the truth of what happened. In these two ends, the glowing shroud and the invisible burst, we see how the universe remembers its dead. It remembers them in color and in silence, in expanding shells and fleeting particles, in bones of calcium and in iron blood. And it is through these remnants and bursts that we, fragile beings on a small planet, learn not just how stars die, but how we came to exist at all. They ripple through the universe not as light, not as particles, but as waves in the very fabric of existence. Gravitational waves are distortions of space-time itself, stretching and squeezing reality as they pass through. They do not burn or glow or collide with gas or dust. They glide across the cosmos almost entirely unhindered, carrying with them the silent memory of the most violent events in the universe. Predicted by Albert Einstein in 1916 as a consequence of general relativity, these waves remained hidden for a century. Einstein himself doubted they could ever be detected. They were too faint, too subtle, like trying to measure the vibration of a spider's web stretched across a galaxy. And yet, 100 years later, humanity heard them for the first time. The concept is as elegant as it is profound. Mass and energy warp the geometry of space and time. When massive objects accelerate, when they orbit each other, collapse, or explode, they generate gravitational waves that propagate outward at the speed of light. These waves stretch space in one direction while compressing it in another, like ripples moving across a pond, but through four-dimensional space-time itself. Most things in the universe create gravitational waves when they move, even two people dancing. But only the most extreme gravitational fields, colliding black holes, merging neutron stars, supernova core collapses, create waves powerful enough to be detected across cosmic distances. On September 14, 2015, two black holes spiraled into each other about 1.3 billion light-years away. For eons, they had orbited in silence, invisible to telescopes, their gravity sculpting nothing but the space around them. In their final moments, they accelerated to half the speed of light, their orbital frequency rising from dozens to hundreds of cycles per second. They merged in less than a heartbeat, forming a single, newly born black hole. In that instant, they released more energy in gravitational waves than all the stars in the observable universe combined emit in light, compressed into a burst that lasted just 0.2 seconds. Over 1 billion years later, that ripple reached Earth. It passed through the planet, faint yet unmistakable, stretching space by less than 1,000th the width of a proton. And deep within two detectors called LIGO, lasers shifted, mirrors trembled, and for the first time in history, gravity was heard. This first detection, known as GW14, changed everything. It confirmed black hole binaries existed. It proved that gravitational waves travel at the speed of light. It validated general relativity in the strongest gravity ever observed. And it transformed astronomy from a science of light to a science of space-time. Since then, dozens of gravitational wave events have been recorded, most from merging black holes ranging from a few solar masses to over 100. Each event is like a cosmic drumbeat, subtle, powerful, and ancient, telling the story of how gravity binds and destroys. Binary black hole mergers are now recognized as the most common gravitational wave sources observed so far. Their origins lie in the depths of massive stars. In some binary systems, both stars are so massive that each collapses into a black hole. If the explosion does not separate them, they remain in orbit, slowly shrinking their separation by radiating gravitational waves. This process takes hundreds of millions, or even billions of years. By the time they merge, they may lie far from their birthplace, in the quiet outskirts of galaxies or floating in intergalactic space. These mergers do not emit light. No supernova, no gamma-ray burst, just gravity. Yet not all binary black holes form from isolated star pairs. Some are born in dense star clusters, where hundreds of thousands of stars live in tight orbits. In these crowded environments, black holes can sink to the center via mass segregation, form binaries through dynamical capture, and eventually merge. These dynamical binaries may have random spin orientations, or even be ejected from the cluster. Others may form in galactic nuclei near supermassive black holes, their orbits distorted by tidal forces until they spiral inward and collide. Each pathway produces different gravitational wave signatures, different spins, masses, orientations, written into the waves like fingerprints. When two black holes merge, the process unfolds in three stages. First is the in-spiral, when they whirl around each other at increasing speed, emitting gravitational waves of rising frequency and amplitude. Second is the merger, an instant when the two horizons join into one, like two soap bubbles touching and becoming a single sphere. Third is the ring down, when the new black hole vibrates like a struck bell, emitting gravitational waves in decaying tones until it settles into a stable, Kerr black hole. These vibrations, called quasi-normal modes, allow physicists to test whether black holes truly follow the equations of general relativity or if hidden physics lies within. After the first detections of binary black holes, the universe offered another gift. On August 17, 2017, gravitational waves from a binary neutron star merger, GW17017, swept across Earth. Unlike black hole mergers, neutron-star collisions produce light. Just 2 seconds after the gravitational waves arrived, a gamma-ray burst lit up satellite detectors. Within hours, telescopes around the world detected a new point of light in the galaxy NGC 4993. It shone blue, then red, then infrared, a kilonova. This was multi-messenger astronomy, gravity and light telling the same story. Astronomers observed not just the collision itself, but the creation of gold, platinum, and other heavy elements. They saw jets emerge and crash into surrounding gas. They even used the signal to measure the Hubble constant, the expansion rate of the universe. All because space-time itself vibrated when two stars died. Future detectors will expand this new science. Ego and Virgo are being upgraded. Kaigura in Japan has joined. LISA, a space-based gravitational wave observatory, will detect supermassive black hole mergers, extreme mass ratio in spirals, and perhaps waves from the early universe itself. Pulsar timing arrays are already hearing ultra-low frequency waves from the slow dance of supermassive black hole binaries in distant galaxies. Gravitational waves have revealed a universe that is restless, dynamic, and violent even in darkness. Light shows us stars and galaxies. Gravity shows us their bones, the invisible structures, the collapsed cores, the dead stars crushing time itself. Through binary black hole mergers, we hear not just the end of stars, but the conversation between mass and space-time. Every detection is both an ending and a beginning. A collision that happened millions or billions of years ago, but whose echo only now reaches our planet. And so, the universe, once seen only in light, now speaks in waves. No longer are we limited to photons. Now space-time itself is an instrument, and we learn to listen to its music. They are among the most exquisite and terrifying events in the universe. Binary neutron-star mergers, where two of the densest objects known to exist spiral together in a death dance that ends in light, gravity, and the creation of gold. Each neutron star is a city-sized sphere of nuclear matter, more massive than the Sun, yet no larger than Ametropolis. Their gravity is so absolute that a teaspoon of their matter would weigh 1 billion tons on Earth. For millions or billions of years, two of these stellar corpses can orbit one another in silence, relics of two massive stars that exploded in supernovae long ago. But as time passes, gravitational waves drain their orbital energy, drawing them closer. They dance faster. Space-time ripples more violently. In the final seconds, they circle each other hundreds of times per second, heating, stretching, deforming, like liquid mountains of neutrons locked in mutual destruction. Then they collide. The impact is unimaginable. The force of gravity crushing matter to extremes never recreated in laboratories. The merger produces a brilliant explosion of gravitational waves, a cosmic chirp that races across the universe. But unlike binary black hole mergers, neutron-star collisions do not unfold in silence. The impact tears apart one or both neutron stars, flinging neutron-rich material into space at a significant fraction of the speed of light. In the expanding debris, heavy elements begin to form through rapid neutron capture, the R process. This is how gold, platinum, uranium, and other heavy elements are born. Moments later, the radioactive decay of these new elements powers a faint but rapidly evolving light, a kilonova. This is not a supernova. It is shorter, stranger, more colorful. In its first hours and days, the kilonova shines blue as lighter R-process elements such as strontium form in regions with fewer neutrons. Soon afterward, as heavier elements like lanthanides and actinides begin to dominate, the ejector becomes opaque. The light shifts to red and infrared. In a week or two, the glow fades into darkness. But in that brief time, more gold may be formed than in the entire history of star formation in a galaxy. For years, astronomers suspected neutron star mergers were responsible for R-process elements, but they lacked proof. That came on August 17, 2017, with GW-17, the first binary neutron star merger ever detected. LIGO and Virgo observed the gravitational wave signal, a high-pitched chirp lasting nearly 100 seconds, far longer than black hole mergers. 2 seconds later, space telescopes saw a short gamma ray burst from the same region. Within hours, optical telescopes identified a new point of light in the galaxy NGC 4993. It glowed blue, then red, exactly like a kilonova should. Infrared spectra revealed heavy elements, strontium and possibly gold. Radio telescopes followed a shockwave plowing into surrounding gas. For the first time in history, humanity observed an event in both gravitational waves and electromagnetic light, true multi-messenger astronomy. It confirmed that neutron star mergers create gold and platinum. It showed how short gamma-ray bursts form. It even helped refine the rate of the universe's expansion. But neutron star mergers are not all the universe has in store. There is an even darker collision, when one neutron star orbits a black hole. Black hole neutron star mergers are rarer, harder to observe, and more violent in their silence. In such systems, a neutron star orbits an invisible companion, too massive to be a white dwarf or star, leaving only one possibility: a black hole. Over millions of years, gravitational radiation pulls them inward. But the outcome of the final merger depends on the black hole's mass and spin. If the black hole is too massive or not spinning fast enough, it swallows the neutron star whole in a single gulp, leaving no matter to escape. No light, no kilonova, only gravitational waves. The universe does not see it happen. It only feels the ripple. But if the black hole is smaller, say 5 to 10 solar masses, or spinning rapidly, tidal forces can tear apart the neutron star before it crosses the event horizon. In that case, a crescent of neutron-rich matter is flung outward, forming an accretion disk and jet around the black hole. A kilonova ignites, redder and dimmer than that of a double neutron star merger. A short gamma-ray burst may erupt along the black hole's axis. The gravitational wave signal is shorter, with a sharper end, an abrupt silence where the neutron star is lost. These events were theoretical for decades. Then, in 2020, LIGO and Virgo detected UP 2001-05 and GW 1001-15, two separate mergers involving black holes and neutron stars. No light was seen from either, suggesting the neutron stars were swallowed whole. But the gravitational waves alone confirmed that such binary systems exist, formed either from massive binary stars or through encounters in dense star clusters. They also hinted at something deeper, that nature forms black holes and neutron stars in many unexpected pairings, and that gravitational waves are the only way to discover them. Binary neutron star and black hole neutron star mergers are not rare quirks. They shape the evolution of galaxies. Each merger contributes heavy elements to interstellar clouds, the gold in wedding rings, the iodine in human bodies, the uranium in Earth's core. In dwarf galaxies, where stars are fewer, a single neutron star merger could enrich entire stellar populations. Some stars in the Milky Way's halo show strange chemical abundances, excess europium or gold, suggesting their ancestors were born from gas seeded by a kilonova billions of years ago. These mergers also birth some of the most extreme objects in existence. A binary neutron star merger might form a hypermassive neutron star, a rapidly rotating object held up temporarily by centrifugal force and thermal pressure. In milliseconds or seconds, it collapses into a black hole. In that brief moment, it could generate magnetic fields stronger than any magnetar, perhaps powering a short gamma-ray burst. The remnants depend on the neutron star equation of state, how matter behaves at densities beyond atomic nuclei. Every gravitational wave from every merger whispers clues about these unknown physics, and the story stretches billions of years into the future. Long after the sun has died, long after Earth is gone, ancient neutron stars and black holes will continue to orbit, spiral, and merge. The universe grows quieter with time as stars fade, but these collisions will outlast entire galaxies. They are the universe's last fireworks, its final storms of gravity and light. In the end, binary neutron star and black hole neutron star mergers remind us of something profound. The heaviest elements of our world, gold, platinum, uranium, were not forged in calm stars, but in the catastrophic embrace of dead suns. Gravity, the same force that holds our feet to the Earth, pulls stars into fatal spirals, crushes atoms into neutrons, and then uses their death to create the building blocks of planets and life. We wear the ashes of neutron stars on our fingers, carry their remnants in our blood, and listen to their final songs in the ripples of space-time. The universe creates, destroys, and creates again. And in the silence between those acts, we learn to hear. They whisper through the universe not as singular events, but as a constant murmur, a faint, ever-present trembling of space-time itself. This is the stochastic gravitational wave background, the gravitational equivalent of cosmic microwave background radiation. But while the microwave background captures the afterglow of the Big Bang in light, the stochastic gravitational wave background holds the echoes of countless collisions, collapses, and cosmic motions stretching across the history of the universe. It is not one wave, but a superposition of many, a cosmic symphony made of overlapping notes from millions of black hole mergers, neutron star spirals, supernovae, and perhaps even quantum fluctuations from the earliest moments of existence. Unlike the sharp chirps of individual gravitational wave detections, the stochastic background is diffuse. It cannot be traced to a single source. It is everywhere and nowhere in particular. It is generated by the combined roar of black hole binaries merging in distant galaxies, too far or too faint to detect individually. It may also come from supermassive black hole binaries at galactic centers, circling each other over millions of years. These giants emit waves with periods measured in years, far too long for ground-based detectors like LIGO to hear. Instead, astronomers use pulsar timing arrays, networks of millisecond pulsars acting as cosmic clocks. As gravitational waves stretch and compress space between Earth and these pulsars, the arrival times of their pulses shift ever so slightly. For over a decade, scientists have tracked these variations. In 2023, several pulsar timing collaborations, including Nanograv, announced strong evidence that they had detected a low-frequency gravitational wave background. If confirmed, it would mean that supermassive black hole pairs throughout the universe are slowly spiraling together, their combined hum forming a gravitational fog across space-time. But the stochastic background may be even older than stars and galaxies. Some theories propose that moments after the Big Bang, during a period of rapid inflation, quantum fluctuations were stretched to cosmic scales, generating primordial gravitational waves. Others suggest that topological defects in the early universe, cosmic strings or domain walls, may have radiated gravitational waves during violent recombination processes. These ancient waves, if detected, would carry information from eras earlier than the cosmic microwave background, times when light could not exist, but gravity could still travel. Future missions, like the space-based LISA Observatory, or even more sensitive pulsar timing arrays, might detect these primordial oscillations. If they do, we may finally glimpse physics beyond the standard model, beyond even general relativity, a window into the universe before atoms, before matter, before time, as we understand it. As gravitational wave astronomy expands, it reveals a universe not silent, but vibrating. Yet even in this new way of listening, something important is missing: most of the universe. For all we can see with light, and all we can now hear with gravity, about 85% of the universe's matter is invisible. This is dark matter. Not dark because it is evil or mysterious, but because it neither glows, nor absorbs, nor reflects light. It is matter that exerts gravity, but refuses to interact with electromagnetic forces. We do not know what it is made of. We only know it is there, holding galaxies together, bending starlight, sculpting the cosmic web. The story of dark matter begins in the 1930s with Swiss astrophysicist Fritz Zwicky. Observing the Coma cluster of galaxies, he calculated that the galaxies were moving too fast to be held together by visible matter alone. There had to be invisible mass, dunkel materia. Astronomers largely ignored him until the 1970s, when Vera Rubin measured the rotation curves of spiral galaxies. Stars at the edges of galaxies were orbiting at the same speed as stars near the center. According to Newtonian mechanics, they should have slowed unless unseen mass was present in enormous halos around each galaxy. Ever since, observations, gravitational lensing, galaxy cluster dynamics, cosmic microwave background fluctuations have all confirmed dark matter's existence. What is it? The standard model of particle physics has no answer. Ordinary atoms, protons, neutrons, electrons, account for only 5% of the universe. Dark matter makes up about 27%. The leading candidates are exotic particles that interact weakly or not at all with light, WIMPs, weakly interacting massive particles, axions, sterile neutrinos. Deep underground laboratories like Xenon 1T or Lux Zeppelin listen for the faintest collisions between dark matter particles and atomic nuclei. So far, nothing definitive has been detected. Physicists also examine data from the Large Hadron Collider, searching for hints of dark matter being created in high-energy collisions. Again, the evidence is silent. Still, dark matter leaves unmistakable gravitational signatures. It forms vast halos around galaxies, spherical clouds of substance we cannot see, but which hold the galaxy in a gravitational grip. Without dark matter, galaxies would fly apart. It forms filaments stretching across hundreds of millions of light years, connecting galaxy clusters in a cosmic web. Simulations of the universe's evolution, like the Millennium simulation, can reproduce the structure of galaxies only when dark matter is included. Astronomers have even observed colliding galaxy clusters, like the Bullet cluster, where dark matter appears to have separated from ordinary matter, mapped only by its gravitational lensing of background light. Alternative theories like modified Newtonian dynamics suggest altering gravity rather than inventing dark matter. But these theories struggle to explain observations on all scales, from galaxies to galaxy clusters to cosmic microwave background data. Most astrophysicists now believe dark matter is real, even if we do not yet know its identity. We live in a universe where most matter is invisible and most waves are silent to our senses. The stochastic gravitational wave background is the unceasing murmur of space-time, formed by the accumulated echoes of distant, unseen collisions. Dark matter is the unseen scaffolding on which galaxies form and evolve. One is a vibration, the other is a weight. One is the music of motion, the other is the architecture of matter. Together, they remind us how limited our perception is. Our eyes see only photons. Our ears hear only air. But reality is deeper, older, stranger. It is woven from gravity and mystery, from waves without light and matter without atoms. The universe speaks, but not always in ways we understand. Yet with detectors buried underground, telescopes in orbit, atomic clocks timing pulsars, and equations scribbled on chalkboards, we are beginning to translate that language. We are learning to see what is dark and hear what is silent. They are the invisible skeletons of the universe, vast, ghostly structures that no eye can see, no telescope can capture. Yet without them, galaxies would fly apart and cosmic order would dissolve. These are dark matter halos, roughly spherical regions surrounding galaxies and galaxy clusters, made entirely of unseen mass. They exert gravity, they shape the rotation of galaxies, they deflect light from faraway quasars, yet they emit no light, absorb no radiation, and cannot be touched or captured. Their existence is known not because they reveal themselves, but because without them, nothing in the cosmos makes sense. Every galaxy, including the Milky Way, sits within a dark matter halo. If we could see ours, it would stretch hundreds of thousands of light years in all directions, enveloping not only the spiral disk of the Milky Way, but the dwarf galaxies that orbit around it. The visible part of the galaxy, its stars, gas, dust, nebulae, accounts for only a small fraction of its true mass. The rest lies invisibly in the halo. Stars near the edge of the galaxy orbit at the same speed as stars near the center, something impossible unless a vast amount of unseen mass is holding them in place. Vera Rubin discovered this when she measured the rotation curves of spiral galaxies in the 1970s, instead of curving downward at the edges, as Newtonian physics predicted. For a galaxy made of visible matter, the curves stayed flat. This meant only one thing. Most of the galaxy's mass was not in its bright stars or glowing gas, but in a halo of invisible matter. On larger scales, galaxy clusters, enormous structures containing thousands of galaxies bound together, show the same mystery. They move too fast, their galaxies flying within them like bees in a hive. Without dark matter, they would disperse. Fritz Zwicky called this invisible mass dunkle materia in the 1930s when studying the Coma cluster. His claim was ignored for decades, but today, with X-ray telescopes, gravitational lensing maps, and galaxy surveys, we know he was right. Dark matter dominates these clusters, forming halos tens of millions of light-years wide. Simulations of the universe's evolution show how dark matter halos form. Tiny fluctuations in the density of dark matter in the early universe shortly after the Big Bang grow over time due to gravity. Dark matter clumps together, forming small halos. These halos merge, forming larger ones. Gas falls into these gravitational wells, cools, and forms stars. Without dark matter, galaxies would not have enough gravity to gather and retain gas. They would never form. It is dark matter halos that allow galaxies to exist in the first place. The structure of a halo follows a pattern described by the Navarro-Frank-White (NFW) profile, discovered in the 1990s through simulations. According to this model, the density of dark matter increases sharply toward the center and falls off unevenly toward the edges. The core may harbor a supermassive black hole surrounded by stars and gas, but most of the mass, the dark mass, remains dispersed, silent, and cold. Sometimes, collisions between galaxy clusters produce visible distortions in halos, though the halos themselves remain invisible. This leads us to one of the most convincing and haunting pieces of evidence for dark matter, the bullet cluster. The bullet cluster, officially known as 1E0657-56, lies about 3.8 billion light-years away. It consists of two galaxy clusters that collided at enormous speed, like two crashing galaxies made not of stars but of entire universes. When they collided, the galaxies within them mostly passed through each other, because galaxies are separated by vast distances and rarely collide directly. The hot gas between galaxies, however, did not pass freely. It slammed together, creating a shockwave seen in X-ray light, a red, bullet-shaped cloud of plasma, hotter than the surface of the sun. If the visible matter, the gas and stars, were all that existed, then the mass of the cluster should align with this glowing plasma. But when scientists used gravitational lensing to map the mass in the bullet cluster, they found something astonishing. The mass was not where the gas was. It was ahead of it, aligned with the galaxies that had moved through the collision. This mass was invisible, showing up only through its gravitational effect on the light of distant background galaxies. The hot gas, which contains most of the ordinary matter in the cluster, lagged behind, like smoke after a bullet. But the dark matter, unaffected by collisions, immune to drag, had kept moving forward with the galaxies. This was the smoking gun of dark matter. Modified gravity theories struggled to explain it. Only dark matter, cold, collisionless, non-interacting, could account for the lensing maps. The bullet cluster was not a theory or a simulation. It was an image of dark matter revealing itself through gravity alone. Since then, other examples have been discovered, like the Trainwreck cluster, Abel 520, and the El Gordo cluster, each displaying the same shocking separation between light and mass, between stars and the invisible. Dark matter halos are not static. They swallow smaller halos, stretching and reshaping as galaxies merge. The Milky Way is currently consuming the Sagittarius dwarf galaxy, its stars being torn into streams while its dark matter halo merges quietly with ours. In billions of years, the Milky Way and Andromeda will collide, their disks shredding, their stars scattering, but their halos will merge, becoming one titanic dark sphere. Galaxies are temporary, halos endure, yet we still do not know what dark matter is. It could be WIMPs, particles heavier than protons but almost non-interacting. It might be actions, feather-light particles that could form waves across galaxies. It might be primordial black holes formed in the dawn of time. Underground detectors wait in silence for a dark matter particle to strike a nucleus. Space telescopes watch for gamma rays from dark matter annihilation near the galactic center. So far, nothing definitive. The universe remains silent about the nature of its dominant matter. And still, dark matter halos bind everything we see. They hold galaxies like snow globes. They lens light from quasars, billions of light years away, bending space around their mass. They cradle galaxy clusters, guide the expansion of the cosmic web, and anchor the motions of stars. We are like fish in a dark ocean, aware of the water only by the currents we feel. Dark matter is that ocean, present everywhere, visible nowhere. The bullet cluster stands as a monument to its existence, a collision not of stars, but of skeletons, dark, silent, enduring. It is perhaps the most compelling proof that most of the universe lies beyond our senses. We map it through lensing, trace its shape in galaxy surveys, and simulate its behavior with supercomputers. Yet we have never held even a single particle of it in our hands. We live in a universe where the stars are just the decorations. The real structure is invisible. They called it a mistake, a blunder, something added to the equations of gravity and then abandoned as unnecessary. And yet, it may be the most powerful force in the universe. Dark energy, an unseen pressure stretching the cosmos wider and wider with every passing moment. The discovery was unexpected, almost unwelcome, because it told a story no one was prepared to believe. The universe is not slowing down. It is speeding up. For most of human history, people assumed the universe was eternal and static. Then came Edwin Hubble in the early 20th century, who showed that galaxies are racing away from us, and the farther they are, the faster they go. The universe was expanding. Astronomers thought gravity pulling on all matter would eventually slow this expansion. The universe might collapse, or it might coast forever, but it would not accelerate. There was no reason to imagine such a thing. No physics required it. No observations hinted at it. Until the 1990s, when teams led by Saul Perlmutter, Brian Schmidt, and Adam Riess used Type Ia supernovae as standard candles to measure cosmic distances. These supernovae explode with almost identical brightness, So by comparing their true brightness to their observed brightness, astronomers can calculate how far away they are. The teams looked not at nearby galaxies, but deep into time, billions of years into the past. What they found was astonishing. The supernovae were dimmer than expected. That meant they were farther away than they should have been if the universe had been slowing down. Instead, the universe had sped up. Sometime around 5 billion years ago, cosmic expansion stopped decelerating and began accelerating. Something was pushing the universe apart. Not matter, not light, something else, everywhere, invisible, smooth, unlike anything previously known. They called it dark energy. Dark energy makes up about 68% of the universe, dwarfing both normal matter and dark matter. It is not a substance that clumps into stars or galaxies. It is not a field that vibrates or radiates. It behaves like a property of space itself, an inherent tension in the vacuum. As space expands, more of it appears, and with it more dark energy, causing even faster expansion. The result is a runaway universe. To understand how something like this could exist, we must return to Einstein. In 1917, when applying his theory of general relativity to the entire universe, Einstein assumed the cosmos was static, but gravity always pulls inward, so he added a term to his equations, the cosmological constant, represented by the Greek letter L, lambda. This constant acted like a repulsive force, counteracting gravity to keep the universe stable. But when Hubble discovered the universe was expanding, Einstein reportedly called L his greatest blunder and removed it. It turns out he was right the first time.